Chapter 1, Apollo 11, an overview of the official version. Lights, camera, action! Between 1968 and 1972, the National Aeronautics and Space Administration NASA launched 11 manned missions on the Saturn V and Saturn V rocket to low Earth orbit. 9 of these manned missions went beyond low Earth orbit using the Saturn V rocket, and 6 landed on the lunar surface, Apollo 11 being the first mission to do so. The Saturn V was a 3-stage rocket that stood 363 feet tall on the launch pad. Each stage of the rocket had a specific function. The first stage was filled with kerosene and liquid oxygen and had 7,653,845 pounds of thrust and was used to launch the Saturn V rocket to an altitude of 36.7 miles. The second stage was filled with liquid hydrogen and liquid oxygen and had 1,120,216 to 1,157,707 pounds of thrust. After the separation of the first stage, the second stage was used to boost the Apollo spacecraft to an altitude of 101.4 miles. The third stage was filled with liquid hydrogen and liquid oxygen and had 178,161 to 203,779 pounds of thrust. After the separation of the second stage, the third stage was used to insert the Apollo spacecraft into a circular Earth parking orbit. The lunar module LM was stored in the spacecraft lunar module adapter SLA located on the top of the third stage, the SIVB. Above the SIVB was the command and service module CSM. The launch escape system LES was fixed to a boost protective cover BPC. The BPC covered the command module CM to protect it from heat friction with air during the first 3 minutes of the launch and from the solid fuel rocket motors of the LES. In case of an emergency, the LES was used to pull the CM away from the Saturn V to safety for an emergency splashdown. A more in-depth look at the testing and performance aspects of the Saturn V will be discussed in Chapter 2. The Apollo 11 astronauts. Apollo 11 was NASA's 5th manned mission in the Apollo program and the 3rd manned mission which left LEO on its mission to the Moon. It was also the first mission to land a crew on the lunar surface. The crew included Commander Neil Armstrong, command pilot Michael Collins, and lunar module pilot Edward Buzz E. Aldrin. For each of the Apollo missions, there was always a backup crew. For Apollo 11, the backup crew consisted of Commander James A. Lovell, command module pilot William A. Anders, and lunar module pilot Fred W. Hayes. Neil Armstrong started flying at the age of 14, paying about $10 for each lesson, which lasted about 1.5 hours. This today amounts to approximately $10 or more for every 5 minutes. He got his pilot's license at 16. In 1947, he was accepted for a naval scholarship and went to Purdue University in Indiana. After 18 months, the Navy sent him to Pensacola in Florida for flight training. In 1950, he flew combat missions in the Korean War. After the Korean War, he continued on for further flight training. In 1952, he resigned from the Navy and enrolled again at Purdue University. In 1960, Armstrong flew the X-15, which could reach altitudes of over 200,000 feet, which he described as akin to being in a spaceship in orbit. After applying to NASA in 1962, in which the organization was now accepting civilian applicants, he was accepted for astronaut training. Edward Eugene Aldrin Jr., aka Buzz Aldrin. His eldest sister, when young, used to pronounce brother as Buzzer, hence the name. Went to the military academy at West Point, New York. After graduating in 1951, Aldrin joined the Air Force and trained as a fighter pilot. He also flew combat missions in North Korea. His gun camera film supposedly showed a pilot ejecting from a MiG he shot down, which was featured in Life magazine. In 1954, after spending 4 months in Maxwell Field, Alabama in Squadron Officer School, he was assigned to the Air Force Academy in Colorado as a flight instructor. In 1956, he went to West Germany to fly the F-100s with the 36 Fighter Wing. After that, he returned to the USA and gained a postgraduate degree at the Massachusetts Institute of Technology, in which he did a doctorate in astronautics. In 1963, Aldrin was accepted by NASA for astronaut training. Michael Collins. Michael Collins went to West Point, Louisiana. After graduating in 1952, he joined the Air Force and was sent to Nellis Air Force Base in Nevada for fighter training. From there, he was stationed in France at a NATO F-56 fighter squadron in 1954. After returning to the U.S. in 1957, Collins was assigned as an instructor. In 1960, Collins enrolled at the Experimental Test Pilot School, Edwards Air Force Base. He was accepted by NASA in 1963 for astronaut training. Armstrong, Collins, and Aldrin had been in the Gemini space program, and two of the backup crew members, Lovell and Anders, also had previous experience in space, most notably as crew members on Apollo 8, the first manned mission to have left low Earth orbit to circumnavigate the Moon. The responsibilities of a backup crew included taking the place of any astronaut who was unable to participate in the mission. The launch. The launch of Apollo 11 took place at 9:32 a.m. Eastern Standard Time, July 16, 1969, from NASA's Kennedy Space Center Launch Complex 39A for an 8-day mission to the Moon and back. After liftoff, the first stage of the Saturn V was jettisoned to about 40 miles in altitude. The second stage was then ignited to boost Apollo 11 to a 100-mile orbital altitude. After reaching the required altitude and the jettison of the first and second stages, the first engine burn or firing of the third stage, SIVB, would insert Apollo 11 into a 100 nautical miles circular lunar parking orbit. After 2.5 hours in Earth's orbit, the SIVB rockets would be fired again, putting Apollo 11 on a translunar insertion, TLI, for a free return trajectory for a 3-day voyage to the Moon. Theoretically, the purpose of a free return trajectory was to ensure that return to Earth in the event of a service module engine failure. A half hour after TLI, the Command Service Module CSM would separate from the SIVB, turn around, and dock with the Lunar Module LM to extract it from the Spacecraft LM Adapter SLA. After docking procedures, the CSM docked with the LM and would have resumed its course toward the Moon for its planned lunar orbit. At this point, Apollo 11 would be put into the Passive Thermal Control PTC mode. This was a slow roll of the spacecraft on its horizontal axis, thus stabilizing the thermal response to solar heating. This will be discussed in detail in Chapter 5. After reaching the Moon, Apollo 11 would then have been inserted into a 60 by 170 nautical mile elliptic orbit. 2 revolutions later, the orbit would have been adjusted to a near circular orbit of 54 to 66 nautical miles. Both of these lunar orbit insertion burns, LOI, would have been made using the CSM's 20,500-pound thrust engine. Lunar orbit and landing. 21 hours after entering lunar orbit, Neil Armstrong and Buzz Aldrin would have entered the LM to check the systems for a descent to the lunar surface. After separating from the CSM, the LM, with Neil Armstrong and Buzz Aldrin on board, would then be put into an elliptical orbit on a perisynthion or low point of 50,000 feet above the Moon. From here, the LM, using its 10,000-pound thrust engine, would have begun its descent for its touchdown on the lunar surface, with Michael Collins remaining in the CSM in lunar orbit. After touchdown on the lunar surface on July 20, 1969, the crew would have prepared the LEM for immediate ascent, and then they would have rested for several hours after depressurizing it for their extravehicular activity, EVA. Armstrong was the first to descend the LM ladder to step onto the lunar surface with his now famous quote, "One small step for man, one giant leap for mankind," although there is now some dispute as to what he actually said. However, for the purposes of this chapter, Armstrong's quote is close enough. Armstrong and Aldrin would spend a total of 22 hours on the lunar surface, with approximately 2 of those hours for EVA. Of these 2 hours, they set up a couple of scientific experiments and collected lunar samples that were brought back to Earth, as well as many photos and videos of their EVA on the Moon. After Armstrong and Aldrin completed their EVA, they then prepared to leave the lunar surface. The LM had 2 basic components, the descent stage and the ascent stage. The descent stage encompassed the landing portion of the LM along with a 10,000-pound thrust engine. The ascent stage had its own 3,500-pound thrust engine. On liftoff from the lunar surface, the ascent stage of the LM separated from the descent stage, using it as a launching pad and leaving it behind on the lunar surface. After liftoff from the lunar surface, the LM docked with the CM 3.5 hours later. Once the LM docked with the CM, all lunar samples and videos were stored on board the CM, and the LM ascent stage was jettisoned from the CM. The latter would have then moved onto its trans-Earth insertion, TEI, for its 3-day voyage back. Again, the Apollo 11 spacecraft would have been put into PTC, and 3 mid-course corrections were planned. The mid-course correction aspect of the mission will be analyzed in detail in Chapter 3. Back to Earth and splashdown. Once Apollo 11 had reached Earth, the CM would have separated from the service module and begun its re-entry procedure by positioning the aft part to enter Earth's atmosphere first. This aft portion of the CM contained the main heat shield needed to protect the astronauts and the CM from burning up due to friction with the Earth's atmosphere. Apollo 11 would have entered Earth's atmosphere at 400,000 feet at 36,194 feet per second. The CM splashed down in the Pacific Ocean approximately 1,000 miles southwest of Honolulu at approximately 12:50 p.m. Eastern Daylight Time, July 24, 1969. All of this, of course, is according to the official records, but there are many unanswered questions and contradictions regarding the Apollo man-moon missions, some of which will be discussed in this book starting with the Saturn V. Chapter 2, the Saturn V rocket. LEO, far as we go. The space program was moved to the forefront of the United States foreign policy when the government was caught off guard by the launch of the first artificial satellite in the world, Sputnik, to low Earth orbit, LEO, by the former Soviet Union on October 4, 1957. This mission was followed by Sputnik 2, launched November 3, 1957, and Sputnik 3, launched May 15, 1958. In fact, when it came to the space program, unmanned or manned, the Soviets were first in almost everything. For example, they were first to have satellites in low Earth orbit, have a man-made object pass near the moon, launch animals to low Earth orbit, launch the first man to low Earth orbit, launch a dual-man mission to low Earth orbit, launch the first woman to low Earth orbit, launch a multi-person crew of 3 to low Earth orbit, have an astronaut leave a space capsule while in low Earth orbit, land a probe on the moon's surface and transmit from there, rendezvous and dock an unmanned spacecraft in low Earth orbit, send small animals to the moon and back, apparently unharmed, and rendezvous and dock between 2 manned spacecraft in low Earth orbit for an exchange of crews. As is apparent, the Soviets were well ahead in the space race with their numerous accomplishments. In fact, for 30 years, from 1957 to 1987, they were first in just about everything when it came to their space program. Everything, that is, except having accomplished the first manned landing on the moon. Today, as of 2018, theirs is the only country in the world with a working manned spacecraft capable of launching astronauts to low Earth orbit to exchange crews with the International Space Station, the ISS. The Soviet firsts prompted the American government to come up with an ambitious plan for gaining superiority over the Soviet space program. This, of course, led to President John F. Kennedy's speech to Congress in 1961 proposing to send a manned mission to the moon and return the astronauts safely to Earth before the end of that decade. So, the American government had to achieve this monumental goal in just 8 years with technology that didn't exist at the time. Also, given the political climate during the Cold War, superiority was the goal, which meant that hubris, not a genuine drive for scientific inquiry, drove both the American and Soviet space program policies. The first man to reach space was the Soviet cosmonaut Yuri Gagarin with Vostok 1, which launched on April 12, 1961. Gagarin subsequently became the first man to orbit the Earth in 108 minutes, during which he reached an orbital altitude of 203 miles. The first American to reach space was Alan Shepard with the Mercury mission launched on May 5, 1961. Shepard's mission was a 15-minute suborbital flight reaching a height of 116 miles. Evidently, the American space program had a lot of catching up to do. After Alan Shepard's mission, John Glenn became the first American to orbit the Earth with the second Mercury missions launched February 20, 1962, almost a year after Yuri Gagarin's historic orbital mission. Glenn stayed in low Earth orbit for almost 5 hours. NASA continued with its manned Mercury space program until 1963. It was almost 2 years before the first manned launch of its second space program with the Gemini missions, which ended in 1966. The purpose of these manned missions was to learn and perfect techniques in preparation for the Apollo moon missions. Further, as the technology evolved with these missions, so did spacecraft capacity, where the Mercury missions was a 1-man crew, Gemini missions a 2-man crew, and Apollo missions a 3-man crew. It became obvious in the Mercury and Gemini missions that automation was a necessary component in any manned mission in low Earth orbit or beyond. Astronauts quickly realized that success in these missions has less to do with their flying skills as military pilots and more to do with automation and the increased need for more sophisticated computer systems. As you'll learn in Chapter 3, the computer systems on the Apollo missions were nowhere near the technology that would have been needed for a successful manned mission traveling 240,000 miles to the moon and the same distance back. After the end of the Gemini manned missions, NASA continued with the Apollo program, which launched the first unmanned Saturn V on February 26, 1966, manned Saturn V with Apollo 7 on October 11, 1968, and unmanned Saturn V on November 9, 1967. The next mission in the Apollo program was the launch of the Saturn V on December 21, 1968, which was the first manned mission of a Saturn V and the first manned mission to circumnavigate the Moon. So, in less than 8 years, NASA has managed not only to match the Soviet space program, but surpass Soviet accomplishments in the space race to achieve what had been called the greatest scientific achievement of the 20th century, with the first manned landing on the Moon's surface with Apollo 11 on July 20, 1969. In the next section, I have provided a brief history of the scientists recruited into NASA and one of the most important contributors to the design and manufacture of the Saturn V rocket. The Apollo Saturn V program. The Apollo program was implemented in order to meet President Kennedy's goal of landing a man on the Moon by the end of the 1960s. This required new and innovative technologies to design and manufacture a heavy-lift rocket, which ultimately became known as the Saturn V. This new design was needed to launch the hardware necessary for a manned lunar landing. The Saturn V was reportedly the most powerful heavy-lift rocket ever built, which produced a combined total of over 7.5 million pounds of thrust in its 5 F1 engines located in the first stage of the Saturn V. There has been no working heavy-lift rocket capable of this power output since the end of the Apollo moon missions. It apparently functioned virtually flawless during the Apollo program from 1969 to 1972. In 1973, NASA decided that it would be cost-effective to design a reusable vehicle replacing the Saturn V. In 1973, NASA decided that it would be cost-efficient to design a reusable vehicle replacing the Saturn V, which was supposed to have been proven technology. Subsequently, the Saturn V program was cancelled after launching the first American space station, Skylab, on May 14, 1973. After several years without a manned space vehicle, NASA launched its first reusable manned spacecraft, the Space Shuttle, on April 12, 1981, 20 years to the day since Yuri Gagarin became the first person to orbit the Earth. However, due to the claims of cost inefficiencies and overruns, the Space Shuttle program was also cancelled in 2011. As of today, NASA no longer has a working manned space vehicle capable of launch to LEO. History. The Saturn V rocket program's origins go back to World War II and the German rocket program with its Vengeance Weapon 1 aeroplane V1 and the Vengeance Weapon 2 rocket V2. The V2 was the first ballistic missile ever built and was used to terrorize London in World War II. The architect of the V1 and V2 was Wernher von Braun, reportedly a brilliant aerospace engineer who, as history records, was secretly moved to the United States from Germany at the end of World War II by the American Office of Strategic Services, OSS, under its program Operation Paperclip. The OSS was a predecessor of the Central Intelligence Agency, CIA. It is estimated that the OSS recruited 1,600 German scientists, engineers, and technicians, while the Soviets recruited an estimated 2,000 German scientists. Wernher von Braun and the other German scientists worked for the U.S. Army on its Intermediate-Range Ballistic Missile (IRBM) program. Later, von Braun and his group were absorbed into the newly formed space agency, NASA. Wernher von Braun and his alleged war crimes. 2 years before World War II, Germany had moved their rocket technology to Peenemünde, a rocket base located on the island of Usedom on the Peene River off the Baltic coast. However, after World War II began, Allied forces launched air raids on Peenemünde, as a result of which this technology, along with the technicians, were moved to other bases around the country, like the underground rocket base at the Middelwerk plant. Serious allegations amounting to war crimes against humanity have been made about personnel of that particular facility, including Wernher von Braun, who was a member of the Nazi Party. During World War II, Germany was using concentration camp prisoners as slave laborers at their Middelwerk plant. An estimated 20,000 slave laborers died from starvation, physical abuse, executions, and brutal working conditions. There has been plenty of debate over the decades about Wernher von Braun's involvement in the estimated 20,000 deaths of war prisoners used as slaves and the deplorable and hellish conditions they had to endure. From Wikipedia. SS General Hans Kammler, who was an engineer, had constructed several concentration camps, including Auschwitz, had a reputation for brutality and had organized the idea of using concentration camp prisoners as slave labor in the rocket program. Arthur Rudolph, chief engineer of the V-2 rocket at Peenemünde, endorsed this idea in April 1943 when a labor shortage developed. More people died building the V-2 rockets than were killed as it by a weapon. Von Braun admitted visiting the plant at Middlework on many occasions and called conditions at the plant repulsive, but claimed never to have witnessed any deaths or beatings, although it had become clear to him by 1944 that deaths had occurred. He denied ever having visited Mittelbrau-Dora concentration camp itself, where 20,000 died from illness, beatings, and intolerable working conditions. There were investigations of some of the scientists recruited by the American government, and it's believed that von Braun himself was questioned about what he knew of the conditions at Mittelbrau-Dora concentration camp. However, all of these scientists' records were expunged by the OSS when they were recruited by the United States, practically ending any paper trail implicating these German scientists, including von Braun. The CIA has maintained that secrecy, although, as the above quote shows, it's now more of an open secret. There were supportedly some witnesses that testified in behalf of von Braun, saying he tried to better working conditions for the slave laborers when possible. However, the veracity of these witnesses and their statements should be considered first before coming to any conclusions. As for Wernher von Braun's Nazi affiliation, proponents of the Apollo mission say that conspiracy theorists use this fact to promote the Apollo mission hoax story. Most serious researchers, who believe these missions to have been fake, separate von Braun's Nazi affiliation and acknowledge his purported brilliance in rocket technology. However, there is a limit to how far that technology will go. Likewise, serious proponents of the Apollo missions also acknowledge von Braun's Nazi affiliation, along with his purported brilliance in rocket technology. The Apollo-Saturn rocket series starts with tragedy. After being recruited into the newly formed space agency NASA, Wernher von Braun was appointed as the director of the Marshall Space Flight Center, MSFC, and as chief architect of the Saturn V rocket. The Apollo program started with the first launch in 1961 involving a variation of the Saturn V rocket, leading up to the first manned mission to land on the lunar surface in 1969. However, when trying to explain each mission and its progress, Apollo mission nomenclature gets a little complicated. For example, the first mission in this series was Saturn Apollo 1 SA-1, not to be confused with Apollo 1, which was a mission simulation of a launch that ended up in tragedy, killing 3 astronauts. There are also the Apollo missions with the prefix AS, not to be confused with SA. To further complicate things, NASA has internal and external designations for each mission. Apparently, the external designations were for the media. In addition, there is a series of 3 books by Eugene Reichel listing each mission in the Apollo program in chronological order, which helps to clarify the Apollo's mission's nomenclature. It is the actual Saturn 1B and most of all the Saturn V which interests us, since these 2 variations involve the first manned missions of the Apollo program to low Earth orbit, to circumnavigate the Moon, and to land on the lunar surface. Leading up to and including Apollo 11, there were 30 missions in the Apollo program. Of these 30 missions, 21 missions involved a variation of the Saturn rocket. Of these 21 missions, 5 were the Saturn 1B and 6 were the Saturn V. However, Apollo 4, the 23rd mission, is where the actual Saturn V missions leading up to Apollo 11 began. Apollo 4 was the first unmanned launch of the Saturn V, but a commonly asked question is, what happened to Apollos 1, 2, and 3? Did they involve the Saturn 1B? No, they didn't even involve a launch, and in fact, this is the part which leads to some of the confusion with these Apollo missions. In order to better answer these questions, let's discuss each mission in chronological order, starting with the Apollo 1 tragedy. Apollo 1. On January 27, 1967 at 1:30 p.m., Commander Virgil Gus Grissom, Senior Pilot Edward White, and Command Module Pilot Roger Chaffee enter the Apollo 1 command module on top of the Saturn 1B for a launch simulation. All 3 astronauts were in spacesuits, and when they were strapped into their seats, the escape tower's protective cover was lowered into position on the CM and locked. The astronauts were, for all intent and purposes, sealed in. Several hours into the launch simulation, at approximately 6:30 p.m., a fire broke out within the CM. While the astronauts were yelling frantically over the communication frequency and desperately trying to open the command module hatch, Technicians outside also tried to do the same, but to no avail. The heat around the CM was far too intense for the technicians to get even close. By the time the technicians opened the hatch, Virgil Gus Grissom, Edward White, and Roger Chaffee had been incinerated. This launch simulation was in preparation for the first manned mission of the Saturn V with Grissom, White, and Chaffee. This simulation mission was then designated posthumously as Apollo 1 in honor of the lost crew. There have been lots of discussions over the decades about this tragedy, as well as some serious accusations leveled at NASA about possible foul play. One theory suggests that Gus Grissom, who more than hinted that the Apollo program was plagued with problems and that it was years away from any attempt at a manned lunar landing, needed to be silenced. However, rather than speculate on this serious allegation, let's instead look at the facts. Gus Grissom was known to be outspoken and was increasingly becoming frustrated with the numerous anomalies within the Apollo program. In a press conference shortly before the tragedy, Grissom hung a lemon on the outside of the command module for the whole world to see, the inference being that the command module was a lemon and not fit for manned space missions. As was common practice with the Mercury and Gemini manned space programs, the command module was filled with overpressurized pure oxygen. Since oxygen makes up about 20% of our nitrogen-oxygen atmosphere, there is enough outside atmospheric pressure at sea level for the lungs to absorb that oxygen into the bloodstream. However, to duplicate sea level pressure in a spacecraft in low Earth orbit would require engineering the hull of the capsule strong enough to withstand sea level pressure against the vacuum of space, as well as carrying the required equipment of nitrogen and oxygen tanks to regulate the mixture. Reinforcement of the CM hull, as well as extra nitrogen and oxygen tanks, would have added weight to the spacecraft, which means more engine power for launch that translates into more propellant and therefore more expense. In order to keep costs down, NASA decided to use pure oxygenated atmosphere and regulate the oxygen environment in the spacecraft to lower levels than at sea level pressure, but with the oxygen pressure content higher, making the transfer of oxygen from the lungs to the bloodstream possible while in orbit. This proved deadly during the simulated launch of Apollo 1 when a spark inside the complex design of the CM caused a fire, turning the oversized pure oxygen environment into a torch, killing the 3 astronauts on board. After the tragic incident, NASA changed the CM environment to 60% oxygen and 40% nitrogen on launch, which decreased slowly on ascent to the eventual pure oxygenated environment over the next day. North American Aviation, NAA, was the primary contractor for the command module. NAA Inspector Thomas Barron had submitted a 500-page report and testified to Congress on April 21, 1967, regarding the anomalies leading up to the Apollo 1 tragedy. 6 days later, Thomas Barron, his wife and stepdaughter were all killed instantly when a train crashed into their car. Since then, Thomas's 500-page report to Congress has disappeared. You can find NASA's internal review report detailing its findings on its website, but there is nothing conclusive to the actual cause of the Apollo 1 tragedy. However, the report does make for some disturbing reading. It seems that no one had seriously considered the hazards of an overpressurized cabin full of pure oxygen. Wikipedia. In the first episode of 2009 documentary series, NASA, Triumph and Tragedy, Jim McDivitt said that NASA had no idea how a 100% oxygenated atmosphere would influence burning. Similar remarks by other astronauts were expressed in the 2007 documentary film In the Shadow of the Moon. These two understated quotes delineate the expertise of NASA's personnel involved in the Apollo program, who were seemingly ignorant to the dangers of an overpressurized oxygenated environment. Note to NASA: it has been established throughout millennia that depriving fires of oxygen is a very effective way of putting fires out. Common sense should then dictate that a pure oxygenated environment is not only a fire hazard, it's a blowtorch waiting for a spark. Apollos 2 and 3. After the Apollo 1 tragedy, Apollo 2 was assigned to a previous mission, AS-202, and Apollo 3 was assigned to AS-203. Therefore, the very existence of Apollos 2 and 3 is up for discussion. Apollo 4. This was the 23rd mission and the first to involve a Saturn V, which was an unmanned mission launched from Cape Canaveral on November 9, 1967. It was a low Earth orbit mission. Duration of this mission was 9 hours. Apollo 5. This was the 24th mission and the fourth to involve a Saturn V, which was an unmanned mission launched on January 22, 1968. It was the first mission to test an unmanned lunar module LM in low Earth orbit, but it should be noted that this particular LEM was structurally incomplete. Therefore, this doesn't qualify as a test on the LM in the actual conditions of spaceflight. Duration of this mission was 11 hours. Apollo 6. This was the 25th mission and the second to involve a Saturn V, another unmanned mission launched on April 4, 1968. Apollo 6. This was the 25th mission and the second to involve a Saturn V, another unmanned mission launched on April 4, 1968. It was a low Earth orbit mission. This mission had significant problems with its 5 F1 engines. Duration of this mission was 10 hours. Apollo 7. This was the 22nd mission, the fifth to involve the Saturn V and the first manned Apollo mission launched on October 11, 1968. Its mission was to test the CM service module SM in the actual conditions in space, in low Earth orbit. Duration of this mission was 11 days. Apollo 8. This was the 27th mission launched on December 8, 1968. This mission should be considered the most significant of three reasons, as it was the first manned, launch of Saturn V, mission to leave low Earth orbit, and mission to circumnavigate the Moon. Up to the launch of Apollo 8, the Saturn V had combined total of only 19 hours of experience in actual conditions of spaceflight, and yet this mission was reported to have been flawless. Duration of this mission was 6 days. Apollo 9. This was the 28th mission and fourth to involve the Saturn V and the second manned mission of the vehicle launched on March 3, 1969. This was the second mission to involve the LM and the first manned mission involving that vehicle. However, this LM should be considered the first test in the conditions of spaceflight since it was a structurally complete version of the vehicle. Duration of this mission was 10 days. Apollo 10. This was the 29th mission, the fifth to involve the Saturn V and the third manned mission of that vehicle, launched on May 18, 1969. It was the second manned mission to leave low Earth orbit to circumnavigate the Moon. It was also the second manned mission of the LEM. While in lunar orbit, the LM separated from the CM. The LM descended to within 50,000 feet of the lunar surface and then aborted the descent to rendezvous and dock back with the CM. This mission was supposed to have been a test run for Apollo 11. Duration of this mission was 8 days. Apollo 11. This was the 30th mission and the sixth to involve the Saturn V and the fourth manned mission of that vehicle, launched on July 16, 1969. It was the third manned mission to leave low Earth orbit to circumnavigate the Moon and involved the first manned lunar landing. Duration of this mission was 8 days. The program continued with Apollos 12 to 17, but the focus of this chapter are the missions leading up to and including Apollo 11. Note: from the 23rd mission on, the duration of each mission of the Apollo series had been rounded off. For the exact durations of these missions, see NASA's website at www.nasa.gov. When one actually studies the details of the Apollo program, it can be seen that aside from testing of the different components of the Saturn rocket on the ground, there was a minimal amount of testing done of the functional Saturn V and Saturn V in the actual conditions of spaceflight before the first manned missions of those vehicles. However, before I talk about the minimal testing of the Saturn V, we must discuss one of the most important aspects of the Saturn V, i.e. the powerful F1 engines. The F1 engines were an integral part of the Saturn V, necessary for the success of an Apollo moon landing mission, and as you'll learn in the next section, the power output of these engines of the Saturn V were overrated. In layman's terms, low F1 engine power means no Apollo moon landings. The overrated power of the FV1 engines. Studies by scientists and engineers outside of the Western engineering and scientific communities that question any aspect of the Apollo missions are usually not publicized in the Western scientific journals or magazines and are, for the most part, ignored. However, it's not so easy to ignore the work of these scientists: Gennady Ivankov, Ph.D., Alexander Popov, Ph.D., Andrei Bolotov, NSG, and S.G. Pogrovsky, Ph.D., in their works, as their work disputes the claim by NASA on the performance of the Saturn V, in particular the F1 engines. The concept of the powerful F1 engines was actually initiated by the Air Force in the 1950s. However, after President Dwight E. Eisenhower established NASA on July 29, 1958, NASA assumed responsibilities for the F-1 engines and awarded the contract for design and production to Rocketdyne. One of the main differences between the Saturn 1B and the Saturn V was their lift capabilities. The first stage of the Saturn V contained 5 F-1 engines, the second stage contained 5 J-2 engines, and the third stage contained 1 J-2 engine. The F-1 engines gave the Saturn V its heavy lift capabilities and the needed power to propel a significant payload, as in the launch of the hardware necessary for a manned landing on the Moon. Without the F-1 engines, the Apollo missions could not have happened, and in fact, that is exactly what is claimed by former Rocketdyne employee Bill Casing over 40 years ago. Minimal testing of the F-1 engines. Rocketdyne had done static testing of the F-1 engines, but it's difficult to ascertain just how many of these static tests were done. I contacted the MSFC for documents regarding static tests of the F-1 engine and was provided with a link to their technical documents. I researched through 300 documents and found out about the F-1 engine, but nothing as to the number of static tests that were conducted. I contacted the National Archives but got no precise information there either. I then decided to contact Rocketdyne, now called Aerojet Rocketdyne, when I found www.thespacereview.com. Their stated purpose. The Space Review is an online publication devoted to in-depth articles, commentary, and reviews regarding all aspects of space exploration, science, technology, policy, business, and more. A posted article on their website about the F-1 engines has this to say: the long-standing story that NASA lost or destroyed the Saturn V plans quickly falls to pieces when one learns about the F-1 production knowledge retention program. This was a project at Rocketdyne, the company that built the F-1 engine, to preserve as much technical documentation about the engine as was possible. This produced about 20 volumes of material on topics such as the engine's injector ring set valves, engine assembly and checkout, and thermal insulation and electrical cables, among others. In fact, lost or destroyed Saturn V documents only add to the suspicion that NASA is hiding something, since these are the very rockets that use the F-1 engines. The author of this article, Dwayne A. Day, then says the goal was to preserve as much technical documentation and knowledge about the F-1 engines as was possible. If that were the case, why not preserve all of it? Day then describes the testing of the F-1 engine. Rocketdyne delivered 98 production engines to NASA, of which 65 were launched. A total of 56 equivalent development engines were tested. The company conducted 2,771 production and R&D firing tests in single engines, 1,100 total full duration tests, and accumulated 239,124 seconds over 66 hours of engine firing experience. The 5-engine cluster used on the Saturn V was fired at the Mississippi and Alabama test facilities 34 times, with 18 full-duration tests for a total of 15,534 seconds of engine experience. Rocketdyne estimated in 1992 that the F-1 engine development program had cost $1.77 billion in FY91 dollars. Dwayne Day also used large numbers to emphasize that there were many tests of the F-1 engines, which when translated, the combined production and R&D firing tests of single engines and full-duration tests of F-1 engines was over 66 hours. The 5-engine cluster test of the F-1 engines was 4 hours in total. There was a combined total of 70 hours of static tests of the F-1 engines, which seems adequate given the duration of each engine cluster after launch, purportedly used in all Apollo missions, which was approximately 2 minutes. This included 35 engine cluster tests, 18 of which were full-duration tests. However, the amount of static testing means little or nothing unless there is a comparable testing of the F-1 engines in actual spaceflight conditions, which is equally, if not more important, for evaluating engine performance, and as you'll see, testing in the unmanned Saturn V missions was nowhere near standards and were minimal to say the least. But before we discuss the overall testing of the F-1 engines in spaceflight conditions, we take a look at some of the disturbing test practices before these engines were assigned to their particular mission. I have chosen these 4 missions for their historical significance in the Apollo programs to highlight this. Apollo 4. The first test firing was on February the 17th, and the program duration of just under 41 seconds met all of the test objectives. Another test was conducted on February 25th, but a red line observer reacted to an incorrect reading by ending the test 83.2 seconds into the planned duration of 128 seconds. The incorrect reading proved to be due to a faulty transducer. After analysis of the results, it was decided that the full duration test would not be needed. S1C1 was refurbished, subjected to a number of inspections and checks by MSCF's laboratories, loaded on the sea-going barge Poseidon, and shipped to KSC. It became the first stage of AS-501, which was launched unmanned as Apollo 4 on November 9, 1967. The first test firing of these engines of Apollo 4 was conducted on February 17 and 25, 1966. These F-1 engines were then stored at the Kennedy Space Center KSC for a year and 8 months before they were used on Apollo 4, and that is without any further testing of these engines. This mission seemingly worked flawlessly. Apollo 6. SIC-2 was installed on the static test stand at MSCF in May 1966. The first test firing on June 7, 1966 lasted for 123.3 seconds. However, on the F-1 engines in this stage, F-4017 showed thrust anomalies. After being removed, it was inspected, refurbished, and subjected to 3 further individual tests, during which it functioned satisfactorily. It was reinstalled at SIC-2 in August. Refurbishment, inspection, and checkout of the stage by several of MSFC's laboratories took several months. It was then loaded on board the barge Poseidon, shipped to KSC in March 1967, and became the first stage of AS-502, which was launched unmanned as Apollo 6. Apollo 6 was launched April 4, 1968, almost 2 years after the recorded test of its F-1 engines. This mission experienced problems with its F-1 engines during launch, which will be discussed in detail further below. Apollo 8. The first SIC to be manufactured by Boeing at the Michoud Assembly Facility in Louisiana was SIC-3, and it was the final stage tested at MSFC. It was shipped by the barge Poseidon from Michoud to MSFC and placed on the static test stand on November 3, 1966. The first test on November 15, 1966 lasted for 121.7 seconds. The stage was removed from the stand on November 21st and returned to Michoud. After refurbishment, engineer change orders, and system checks, NASA accepted it for shipment to KSC. On arrival there on December 27, 1967, it was placed in storage. It became the first stage of AS-503, which was to be the third unmanned test flight of the Saturn V. But when this was cancelled, the vehicle was used for Apollo 8, the first manned mission which flew out to orbit around the Moon. The F-1 engines were stored for over a year without any further testing before they were used to launch Apollo 8, and in just 7 months the problems that plagued Apollo 6 were resolved before the first manned mission of Apollo 8, which was seemingly flawless. Apollo 11. On March 1, 1968, SICS arrived at the Mississippi Test Facility on the barge Pearl River. It was installed in the B-2 stand on March 4th and subjected to months of checkout and tests. Finally, on August 13th, it was fired for a planned 125 seconds. All F-1 engines performed within their performance parameters. This test was particularly significant due to the inclusion of the POGO suppression system added after Apollo 6 suffered from the longitudinal oscillations when launched on April 4th. Following the post-fire checks, the stage was returned to Michoud on August 28th for refurbishment, modification, and checkout. On 16 February 1969, it was loaded onto the barge Orion for shipment to KSC, where it arrived 4 days later. SIC-6 is perhaps the most historically significant of the Saturn V first stages because it was stacked as SA-506 and launched as Apollo 11, the mission that achieved Kennedy's challenge of landing men on the Moon. It seems that there were no more test firings of the F-1 engines after August 1968, which was touted to be the most historically significant mission in the Apollo program, as well as the greatest scientific achievement of the 20th century. The previous 4 quotes are from the same book on the F-1 engine. In a review of that book, Jeff Faust has this to say: Young relies on a combination of primary sources, including NASA and Rocketdyne documents, as well as oral interviews with people who worked on the F-1 engines, who provided additional insights and anecdotes that cannot be found in the original documentation. Contrary to what Dwayne A. Day has to say regarding the F-1 production knowledge retention program, it's apparent that decades later, it's up to people who worked on the F-1 engines to fill in the missing data from incomplete documents. Further, as mentioned earlier, it is the lost or destroyed Saturn V documents that are needed to substantiate any of the data related to F-1 engine static tests. In addition, NASA knew that in the early 1960s that the F-1 engines were not up to the task of launching the required Apollo hardware for a manned lunar landing. Former Rocketdyne employee Bill Kaysing exposes the F-1 fraud. The first person to expose the F-1 fraud and simultaneously the Apollo moon hoax was Bill Kaysing, who published a book on it in 1976. Bill Kaysing was an employee of Rocketdyne and had direct access to the documents pertaining to the F-1 engine tests. He was an employee of Rocketdyne from 1956 to 1963, a period which coincides with the first static tests of the F-1 engine. Wikipedia. Kaysing began work as a senior technical writer at Rocketdyne starting on February 13, 1956. On September 24, 1956, he became a service analyst. Starting September 15, 1958, he worked as a service engineer, and starting on October 10, 1962, as a publications analyst. On May 31, 1963, he resigned for personal reasons. Trained as neither an engineer nor a specialist, he nevertheless also served as the company's head of technical publications during his time from 1956 to 1963 at Rocketdyne, a division of North American Aviation, and from 1967 of Rocketdyne International, where the Saturn V rocket engines were designed and built. Bill Kaysing's decision to resign from Rocketdyne had a lot to do with what he saw in the F-1 engine's documents. And aside from the fact that Kaysing was not trained as an engineer nor a specialist, as Wikipedia is quick to point out, it's apparent that Rocketdyne was impressed enough with his expertise to hire him to analyze reports. It follows that Kaysing was more than qualified to read technical documents and evaluate data regarding the F-1 engines. During his employment at Rocketdyne, Kaysing claims to have seen evidence in these documents that the F-1 engines of the Saturn V were not capable of producing the power output needed to launch the Apollo hardware into low Earth orbit for the lunar missions. This is significant since NASA, after much debate, adopted the method of lunar orbit rendezvous (LOR) for a lunar landing, which required NASA to launch the Apollo lunar hardware as well as the astronauts in one mission, as opposed to launching the lunar hardware in a separate mission. This, of course, would have required the purported heavy lift capabilities of the F-1 engines in the Saturn V. Kaysing had been criticized and ridiculed over the decades, and sometimes in less obvious ways, as with the Wikipedia quote above. However, Kaysing was never deterred, and for the last several decades, he maintained his claims that the real power output of the F-1 engines was far less than NASA claimed. Bill Kaysing writes, "From the date of the decision to simulate, the modified hardware program was conducted. For example, the Saturn V moon rocket assembly was built to specifications with one major modification. Instead of total unreliable F-1 engines, the 5 rocket engines of the more dependable B-1 type as used in the C-1 cluster for the Atlas missile were used. Although a cluster of B-1 engines produced only one half of the output of the single F-1 engine chamber, the power, that is, 750,000 pounds of thrust, was sufficient to launch the virtual empty Apollo vehicle. If the rocket had been in its design form, it would have weighed 6 million pounds, or 300 tons fully loaded. This is the weight of a U.S. naval destroyer, further pointing out the total impracticality of the venture. However, by eliminating every aspect of the moon voyage, fuel, heavy machines, LEM vehicles, etc., the total weight of modified, short-range, simulated voyage Apollo was less than 1/20th of the original, or about 150 tons. This loading was well within the capabilities of the B-1 propulsion units. Also, since the originally planned 2 million parts were reduced to a mere 150,000 gadgets, the success of the limited mission was virtually assured. However, even the C-1 Atlas engines were known to explode on the pad or shortly following launch. Thus, the escape module for the astronauts was left intact and functioning. If there had been an accidental loss of thrust or other mishap, it would have been simple to have the saved astronauts merge from the escape module after its recovery. Note: to clarify, the C-5 was eventually changed to the Saturn V. Bill Kaysing may have gotten some of the details in his book wrong, for example the actual mechanics of the modified Saturn V, but his overall point that the F-1 engines did not have the heavy lift capabilities that has recently been substantiated by the previous mentioned scientists Ivankov, Popov, Bultov, and Progrovsky. It's obvious that what Bill Kaysing initially saw in these F-1 engines documents was either deleted from the record or the original documents have gone missing, and since the power output of the Saturn V engines were not what NASA had claimed, they, by inference, NASA fabricated future documents, that is, if any of this data even existed. Engineer Gennady Ivchenkov, Ph.D., substantiates Bill Kaysing's claims. Gennady Ivchenkov published a 55-page article on the performance of the F1 engine. His premise is that the combustion chamber of the F1 engine was unstable, meaning that the F1 engine could not have used its full power potential. Gennady Ivchenkov writes, "The question of whether the Saturn V rocket engineers corresponded to NASA's stated characteristics is directly related to the Apollo moon hoax. Did the Americans really go to the moon in 1969-72, or was it an elaborate hoax? This question was raised initially by the Americans themselves, almost immediately after the Apollo missions. Over the years, a considerable amount of direct and indirect evidence has come to light that at least some of the missions were in fact staged. One of the aspects of this indirect evidence Ivchenkov talks about is NASA's marketing publications, in which chief designers of the Soviet space industry had no trouble deciphering what the actual power output of the F1 engines was, not as NASA claimed. Further, as Ivchenkov says, it is only recently that documents have become available that contradict the claims made by NASA. So, it seems that some of the original data for the F1 engines did exist and did survive, validating Bill Kaysing's claims. For the general public, there are sources of information in technical books and articles detailing the different aspects of the Saturn V and its F1 engines. However, one should be cautious as to the reliability of any of the data in these sources. Regarding quotations, all technical information in North America, including technical guidelines, manuals, instructions, etc., is written by so-called technical writers who put the available material into literary form accessible to the public. It's just a job, something like a journalist writing on technical subjects. It is easy to distort the source material. 7 inconsistencies for the F1 records are noted later in this article. Therefore, all numbers and technical data in such documents should be treated with caution. Note: many journalists have written on technical matters and have done so accurately in accessing documents where necessary. However, it would be incumbent on the reader to carefully check the financial backing and sources of any of the numerous investigative journalists who publish such material. Proponents of the Apollo missions are quick to point out that these documents can be accessed at various online sites such as MFFC, NASA, and the National Archives, but many of these documents are incomplete or are missing, and any of these documents that still exist could easily be translated and published into books placed in public libraries, as well as being stored away, example, in the National Archives. Also, a lot of these technical books are based on interviews conducted decades later with personnel who were involved with the Apollo missions and rely more on memory since documents are either incomplete or missing. Regarding the F1 thruster chamber, the thrust chamber body provides a combustion chamber for burning propellants to generate pressure and an expansion nozzle to expel the combustion gases at high velocity to produce thrust. The combustion chamber of the F1 engine produced thrust nearly 10 times greater than any previous rocket engine. The temperature of the combustion chamber extension reached 5,900 degrees Fahrenheit and thus needed to be cooled. The material that cooled the combustion chamber was provided by tubes running along the combustion chamber walls. The tubing material needed to be strong enough to withstand the thrust force, yet light enough to minimize the overall weight of the Saturn V. Fuel enters the fuel inlet manifold through 2 inlets set 180 degrees apart. From the manifold, 70% of the fuel is diverted through 89 alternating corrosion-resistant steel down tubes the length of the chamber. A manifold at the nozzle exit returns the fuel through the remaining 89 up tubes to supply the injector. A manifold at the nozzle exit returns the fuel through the remaining 89 up tubes to supply the injector. The fuel flowing through the tubes provides regenerative cooling of the chamber walls during engine operation. It is the material used to make these tubes that cause the combustion chamber instability. As the analysis of Ivchenkov's article shows, the source gives the thickness of the F1 tubes as 0.475 mm, the accuracy of which is highly questionable, since such a wall thickness contradicts the cooling requirements. The combustion chamber tubes were made of thin-walled tubes of nickel alloy in Coronal X750, which differ from what was used in the seemingly successful H1 engines in the Saturn V. As Ivchenkov explains, when using the Coronal 750, this material could not have withstood the pressures and temperatures produced by the F1 engine thrust. In this case, the combustion chamber thrust would have been throttled back, which means the Saturn V could not have lifted the necessary Apollo hardware into low Earth orbit for a manned moon landing mission. A NASA report regarding a static test of the F-1 engine in 1959 is quoted in Chenkov's article shows that the F-1 engine did indeed produce the necessary thrust, but with a catch. In January 1959, Rocketdyne's NASA contract included requirements for a series of feasibility firings of the new F-1 booster. 2 months later, the engine hinted at its future success with a brief main stage ignition. The trial run demonstrated stable combustion for 200 milliseconds and achieved a thrust level of 5 million newtons, 1 million pounds. In conducting these tests, Rocketdyne used a solid-wall boilerplate, thrust chamber, and injector, a far cry from flight hardware, but the unheard-of mark of 4,500,000 newtons, or 1 million pounds of thrust, had been reached by a single engine. The catch being the sustained static test firing did not match the duration of the Apollo launch up to the separation of the first stage of Saturn V, which contained the F-1 engines. This is an important point to remember, keeping in mind the actual conditions of spaceflight. This is obviously an example of what Bill Casing was talking about when he stated that the F-1 engine's firing tests could not be sustained. Rocketdyne had built several facilities for static testing of the F-1 engines. The Bravo Stand test facility at Santa Susana Field Laboratory was used for the F-1 components testing. But because of the noise and close proximity to housing, future static tests of the F-1 engines were conducted at Edwards Field Laboratory, away from civilian and of course out of sight of the public and the media. And although F-1 engine static tests were subsequently done, that's a far cry from actual flight hardware and from using a cluster of F-1 engines in actual spaceflight missions using the Saturn V. It is also difficult to determine or access the power output data of the F-1 engine static tests leading up to the first Saturn V launch. There was even less testing in actual flight conditions using the F-1 engines in the Saturn V, which will be discussed in the next section. As has been previously mentioned, Apollo 6, the unmanned second launch of the Saturn V, experienced several problems during its mission. Unlike the first launch of the Saturn V, which had been almost flawless, this mission ran into difficulties from the very beginning. The reasons was pogo oscillations, which caused various degrees of damage. During the first stage flight, a panel of the payload fairing separated because of vibration and expanding moisture in the structure. While the second stage was operating, failures in the fuel lines caused 2 of the 5 engines to shut down prematurely, which resulted in the third phase of the payload reaching suboptimal orbit. Instead of the desired circular orbit at 118 miles, it achieved an elliptical orbit with a lowest point of 107 miles. The above quote gives the impression that it was anything but the fault of the F-1 engines, instead blaming the problem on the pogo oscillations of the Saturn V. If Apollo 6 had been an actual mission, it would not have been able to proceed on its trajectory to circumnavigate the Moon, given that it did not reach optimal orbit. Further, any attempt to increase its orbit in the last-minute attempt to salvage the mission would have been out of the question anyways, as the third stage J2 engine also failed. In analyzing documents for the J2 engines, as well as photos of the Apollo 6 launch, Chenkov observes, various documents and others state that the Apollo 6 and the Apollo 13 had problems with the J2 engines on the second and third stages. The J2 papers mention several cases of cooling tube breakthroughs, but in the available F1 documents there is no such information. At the same time, on the picture of the Apollo F1 flight, it is obvious that one or more F1 motors of the first stage are burning. Kerosene is leaking, catching fire, and forming a huge tail of flame and soot. Thus, it turns out that NASA, for whatever reason, has not provided complete information about these F1 problems. Considering that the Apollo 6 damage, essentially related to the design of the F1 engine, occurred 7 months before the Apollo 8 mission, and it can be concluded that there was no time for fine-tuning of the engine to the declared characteristics. NASA has inferred that it was the pogo oscillations that caused the F1 engine problem, when in fact it was the opposite. A problem with the F1 engines caused the pogo oscillations, but now we can learn that there were problems with the J2 engines as well. This is another significant point, since the J2 engines would have been needed to boost the Saturn V to LEO and the trajectory for the Moon mission. As further stated in Ivgenkov's article, NASA may have attempted to utilize the full power of the F1 and J2 engines with Apollo 6, which led to numerous problems after launch, which required the reduction of power to minimize damage and prevent an explosion. The irony here is that it was most likely the design of the tubular cooling system that was responsible for the combustion chamber instability, which prevented the use of full power in the F-1 engines and inevitably prevented an explosion on Apollo 6 during launch. Therefore, for a successful mission, and in the absence of problems experienced with Apollo 6, the initial thrust of the F-1 engines, if they were used, needed to have been throttled back, defeating the F-1 engine's stated purpose, which was to launch the Apollo hardware into low Earth orbit for a manned lunar landing mission. Any power in the F-1 engines lower than what NASA has stated would have meant that there were no manned moon landings, meaning all Apollo missions outside of LEO were faked. Apparently, after solving the instabilities of the F-1 engine combustion chamber, the actual cause of the problem seems to remain elusive. The spontaneous combustion instabilities never reappeared. Until the end, however, the problem was never completely understood. To this day, it remains a constant problem in the large rocket engines for which an individual empirical solution has to be found. To the disappointment of the engineers, a model was never found in which they could generally overcome the problem. NASA admits it did not know what caused the problems with the F-1 engines, yet it says the problem was overcome as they worked perfectly during the Apollo missions. However, after 1973, the remaining F-1 engines were never used again. The issue is not whether the F-1 engines existed or not, as there's evidence that they did, and NASA even has the F-1 engines in storage and on display in museums. The issue is whether or not they had the required power output, as NASA claims, and whether they were used in the Saturn V. The preponderance of the evidence now shows that the F-1 engines didn't have the power output needed to launch the hardware to low Earth orbit for a successful manned lunar landing. The next mission after Apollo 6 using the Saturn V was Apollo 8. As previously mentioned, Apollo 8 was the first manned mission of that vehicle and the first manned mission to leave low Earth orbit to circumnavigate the Moon. All of the problems experienced with Apollo 6 were seemingly solved in just 7 months. However, as Evgenkov points out, 7 months would not have given Rocketdyne and NASA enough time to have worked out the problems that were observed with Apollo 6. He further states that Apollo 6 may have actually been the first and last mission of the Saturn V to use the 5 F-1 engines. Gennady Evgenkov concludes, the pressure in the F-1 combustion chamber is likely to have been significantly lower than stated due to the fundamental shortcomings of the tubular cooling system of American rocket engines. This is further confirmed by the fact that all rocket engines now being developed and currently in use, including those in the United States, use the Soviet-styled cooling system. Consequently, the launch weight of the Saturn V was lower and accordingly could not have ensued the accomplishments of the Apollo moon landing program. Nevertheless, although the F-1 engines produced smoke, they worked. They were not exploding in front of the public and were delivering something to somewhere. In general, we can express admiration for the Rocketdyne engineers who managed to get at least some characteristics of this miracle in an American mastermind, the F-1, as even 500 tons of thrust per chamber is still quite a lot. The true F-1 design and its characteristics, apparently, were significantly different from those stated. To reiterate, NASA no longer uses a cooling system in its rocket engines that worked seamlessly perfect during the Apollo moon missions from 1969 to 72, preferring instead to use a Soviet-style cooling system. The Western scientific community has since tried to counter S.G. Pogrovsky's work with the book Moon Hoax Debunked. Finally, a no-nonsense, fact-filled rebuttal of moon hoax claims for doubters and enthusiasts alike by Paola Atavissimo. It is a book that should be read, as it is important to read both sides of this discussion. Note: you can read Paola Atavissimo's counter-argument regarding the Saturn V's performance in his book on owlist.com. But the exact facts surrounding the performance of the Saturn V can never be determined, since most of the fact-filled documents have disappeared. Minimal testing of the Saturn 1B and Saturn V. As stated, Apollo 4 was the first mission involving the Saturn V, was also the first mission to supposedly have the cluster of 5 F-1 engines. There was only one more mission, Apollo 6, which involved the F-1 engines, but this mission was plagued with problems. We now know that subsequent missions involving the Saturn V either used reduced power in the F-1 engines due to instability of the combustion chamber, or instead used different engines with less power and thrust. Either way, the Saturn V lacked the power necessary for launching the Apollo hardware into low Earth orbit for a manned lunar landing. We will now look at the minimal testing of the Saturn V with its F-1 engines in the actual conditions of spaceflight. The Saturn V and Saturn V were very different when it came to factors like capabilities on launch, the effects of atmospheric forces, and the trajectory to low Earth orbit and beyond. Hence, both the Saturn 1B and Saturn V cannot be combined in total spaceflight experience since their characteristics are different. Further, it was the Saturn V which contained the F1 engines needed to launch the Apollo hardware into low Earth orbit for a manned lunar landing. This makes the overall minimal testing of each of these two Saturn rockets in actual spaceflight, especially that of the Saturn V, all the more startling. Most of the previous missions leading up to the first manned mission involving different components of the Saturn V series, not the complete structure of the Saturn 1B or Saturn V itself. The 20th mission was the first launch of an actual Saturn 1B, and the 23rd mission was the first launch of an actual Saturn V. Both of these missions were unmanned. There were only 5 unmanned missions of the Saturn 1B in actual conditions of spaceflight before the first manned mission of that vehicle with Apollo 7 to low Earth orbit. There were only 2 unmanned missions of the Saturn V with a combined total duration of 19 hours before the first manned mission of that vehicle. But when you look further into the testing of the Saturn V, the first stage with its F1 engines had only a combined total of approximately 4 minutes in actual conditions of spaceflight before the first manned mission of the Saturn V with Apollo 8. This is very surprising since we were led to believe that Apollo 8 circumnavigated the Moon and was apparently a flawless mission. The MFSC had built scale models of both the F1 engines and the first stage of the Saturn V for wind tunnel testing, which were used for simulating launch by decreasing atmospheric pressure from approximately 20 to 37 miles in altitude. Aviation used the same method, but this was always followed by many hours of testing in actual flight conditions, and as we've seen, NASA in no way matched that level of spaceflight testing. This becomes quite obvious when you compare NASA's testing of the F1 engines in actual flight conditions, which amounts to mere minutes, to the testing of each new aircraft in actual flight conditions, which amounts to hundreds of hours. Given NASA's purported proficiency in automation, with numerous unmanned and automated missions to low Earth orbit and beyond, including 2 unmanned missions of the Saturn V, Apollo 8 should have been another unmanned and automated mission, especially given that it was the first Apollo mission to leave low Earth orbit to circumnavigate the Moon. This should have been followed by further automated and unmanned missions using the Saturn V to circumnavigate the Moon in order to accumulate as much data as possible. Data from the Saturn V unmanned missions could have then been studied meticulously, making design modifications where necessary before sending the first manned mission outside of low Earth orbit, therefore increasing the chances of success, like we have been led to believe happened with Apollo 8. This would have been a logical first step. NASA then could have launched a series of unmanned and automated Saturn V's complete with the necessary hardware for lunar landing, again to accumulate as much data as possible. These data from automated lunar landings could have been studied, making any design modifications necessary, increasing the success for the first manned lunar landing, as we were led to believe happened with Apollo 11. This would have been a logical second step. Although there had been unmanned landing missions on the lunar surface by both the Americans and the Soviets at that time, it is important to note that up to the Apollo 11 mission, there was nothing of that magnitude of an Apollo 11 landing. It would have made sense to have numerous unmanned and automated landings with the LM on the lunar surface, aside from computer simulations and the use of the Lunar Landing Research Vehicle, LLRV, and the Lunar Landing Training Vehicle, LLTV, used by astronauts as part of their training to simulate lunar landings. There will be an in-depth discussion of this in part 2 of this series. Software simulations were limited with 1960s technology, but as NASA claims, they had access to the AGC on the Apollo missions from Mission Control. So, they could have easily practiced unmanned lunar landing procedures using the Apollo LM in the actual conditions of spaceflight before the first manned landing. In addition, there were only 4 unmanned missions of the CM and 5 unmanned missions of the SM in the actual conditions of spaceflight before the first manned mission of Apollo 7. The SM would have been a vital aspect of the Apollo missions, given that it was responsible for providing life support systems and propulsion. NASA had 2 vacuum chambers, which simulated the vacuum of space large enough to test the CM and SM. But that doesn't compare to the actual conditions of spaceflight in low Earth orbit and beyond. Apollo 8, along with being the first manned mission to use the Saturn V with its cluster of 5 engines, was only the second manned mission of the CM and SM. Further, Apollos 9 and 10 don't amount to much in any way of combined experience for Apollo 11 either. One could argue that the manned Mercury and Gemini space programs should be added in terms of experience along with Apollos 7, 8, 9, and 10, which would amount to approximately 2,000 hours of experience in actual conditions of space leading up to Apollo 11. But that experience should only be applied to astronauts in terms of the human experience in space, since it didn't involve the same design and configuration of the Apollo spacecraft, nor did any of the Mercury and Gemini manned missions involving going beyond low Earth orbit. It is the actual missions involving the Saturn V that were paramount. The Saturn V, CM, SM, and LM were more complex in their design, supposedly incorporating new and innovative fly-by-wire technology. Although fly-by-wire technology was already used in the military aircraft at this time, the Apollo missions were the first to use an integrated fly-by-wire computer system. Therefore, when it came to the testing of new technologies, the same standards used in aviation should have been applied to manned space missions, but obviously this was not the case. In addition to NASA using scale models of the F1 engines and the Saturn V, they were also running computer simulations at the same time when software necessary to run computer simulations was limited. And unlike aviation, which has decades of experience behind it, NASA's manned spaceflight missions to low Earth orbit had only a few years of experience, and manned missions beyond low Earth orbit were non-existent. Chapter 3: Navigation and the Apollo Guidance Computer. Has anyone seen Earth? The Apollo mission's method of navigation was what piqued my interest and motivated me to begin my research. It was a method based on celestial navigation that had been used by ships sailing across the oceans for hundreds of years. It is one thing sailing around the world using this method with established geological landmarks and maps, but quite another when you consider the vast distance relative to our technology when making a 480,000-mile round trip in cislunar space. Even with 1960s technology, such as the much-touted Apollo Guidance Computer, AGC, which was a fly-by-wire system incorporated into this method of celestial navigation, you'll learn how challenging it would have been to even try navigating in low Earth orbit, let alone a 480,000-mile round trip in cislunar space. The relatively new, for that time, fly-by-wire technology used in the Apollo missions had been in use in the military aircraft since the 1950s, but the fly-by-wire AGC was the first fully integrated system used on any manned mission, let alone in low Earth orbit and beyond. I pared down the description of this technology in the next two sections for a better understanding. Fly-by-wire. Today, fly-by-wire technology has become common in the airline industry. In aircraft, fly-by-wire technology has eliminated the need for hydraulics to move control surfaces like the rudder, elevator, and ailerons. For example, in previous aviation technology, the pilot would make inputs on the control column to activate the hydraulics, which would move or deflect the ailerons on the outside of the wings to bank the aircraft. This technology has now been replaced in new aircraft like Airbus and Boeing. So, when the pilot makes inputs on the control column, he or she is commanding the computer to send a signal to an actuator to bank the aircraft, replacing the need for hydraulics. Since there are no hydraulics, this method should ideally save on weight and fuel costs, although given today's greed among oil companies, those savings are usually nil. The first fully integrated use of a fly-by-wire system with no mechanical or hydraulic backup system was the Apollo Lunar Landing Research Vehicle, LLRV, which was first flown in 1964 and was used for training the Apollo astronauts. The LLRV was configured to simulate the LM in 1/6 gravity for lunar landing practice. This technology was then incorporated into the Apollo spacecraft design. The LM's fly-by-wire system was tested for the first time at actual conditions in low Earth orbit with Apollo 9 in March of 1969. The second test of the fly-by-wire system in actual conditions with the Apollo 10 in lunar orbit to a descent to within 50,000 feet of the lunar surface in May 1969. Both of these missions were supposed to have been a test run for Apollo 11. Any and all anomalies with the fly-by-wire AGC managed to be sorted out in just 4 months, with only 2 Apollo missions in the actual conditions of spaceflight. The first civilian aircraft to use fly-by-wire technology was the Concorde in 1969, which entered commercial service in 1976. The manufacturers of Concorde decided to err on the side of caution and tested their aircraft's fly-by-wire system for 6 years before allowing any passengers on board. Apollo Guidance Computer. The AGC was designed by the Massachusetts Institute of Technology, MIT, and manufactured by Raytheon. Each Apollo mission had two of these computers, one for the CM and the other for the LM. The AGC evolved from navigating the CM to the Moon and back to a fully integrated fly-by-wire computer system responsible for attitude, the reaction control system, RCS thrusters for trajectory, and the service propulsion engine of the CM. The AGC had three main components. 1. The inertial measurement unit, IMU. 2. The optics containing a sextant and scan telescope. And 3. A computer to integrate the systems including the guidance, navigation and control, GN and C system. The inertial measurement unit. The inertial measurement unit, IMU, was responsible for detecting the internal motion of the spacecraft. It consisted of three swivel gimbals which contained spinning gyroscopes to hold them in place as the spacecraft's position orientation changed. The principle is the same as the gyros installed in aircraft flight instruments, especially in general aviation, although this is now being replaced with the new glass cockpit technology, much like the airliners have been doing for the last couple of decades. For example, the attitude indicator in an aircraft is a gyro instrument with an artificial horizon as a reference for the pilot. The attitude indicator remains fixed in reaction to the ground with the aircraft moving around the instrument, therefore giving the pilot pitch, bank, and roll information. With the Apollo spacecraft, this inertial space was in reference to the stars, and given that the Apollo astronauts were military pilots, they requested that a similar instrument be installed in the CM and LM. This was called the Flight Director Attitude Indicator, FDAI, displaying pitch, yaw, and roll angles with the instrument displaying Earth and Moon's horizon to give the astronauts a better sense of orientation. The optics. As part of the navigation system, the Apollo spacecraft had a version of a sextant called the optics, which was used by sailors for hundreds of years to measure angles between the Earth's horizon, the Sun, and the stars. It consisted of a sextant and telescope. The former was an optical instrument capable of measuring angles between two stars. The lens had a 1.6 negative degree true field of view with 28 times magnification and two lines of sight used for star sightings, one fixed called the landmark line of sight, LLOS, and one movable called the star line of sight, SLOS. The LSOS swung up to 57 degrees from the fixed line of sight and was used to bring the star sightings into alignment with the Earth's horizon. Usually, two star sightings would be sought out and the coordinates fed into the AGC. The telescope part of the optics had a 1 times magnification with a 60-degree true field of view. Since the optics was fixed in position, the AGC would be commanded to position the CSM for star sightings. The Command Module Pilot, CMP, would then aim the telescope at a star and line it up with the sextant. Among programs stored in the memory core of the AGC was a list of angles for 37 bright stars more easily visible to the astronauts. After the CSM was positioned, a program was selected for aligning the IMU. The CMP would then press a switch for the computer to read the angles between star sightings taken by the optics. This would display the angles on the display and keyboard, DSKY, and then used to realign the IMU. From this information, the CMP would obtain the state vector and determine whether a course correction was necessary. This procedure for checking the state vector was done several times on Apollo 11 on the way to the Moon and back. Guidance, navigation, and control system. NASA wanted this new computer to have an autopilot as well as guidance and navigation capabilities, so the computer further evolved into the Guidance, Navigation, and Control System, GN and C, commonly referred to as the AGC. Raytheon had to pare down the usual floor-to-ceiling computers of the 1960s to the one size of a cubic foot, approximately for the CM and the LM. This supposedly was accomplished in just over 1 year. The AGC did not store information on a disk. It was stored in read-only memory, ROM, which was a core rope memory system. This was accomplished in the manufacturing phase by weaving copper wire through and around a tiny magnetic core. The crew interfaced with the AGC using a digital display and keypad known as the DSKY, pronounced disk key, on board both the CM and LM. Mission Control at Houston also had a disk key to interface with the AGC for remote control, if when necessary. Software for the AGC was written in binary, assembly, or machine language. The interpreter was used to translate mathematical functions, and the executive managed the programs. NASA claims that the AGC was capable of running several programs at the same time. And although NASA claims that the AGC had autopilot, it did not have autonomous capabilities for finding solutions to the many scenarios that could have endangered the Apollo missions and, of course, the astronauts. Trajectory and docking using the non-autonomous AGC. One of the many important procedures for the Apollo spacecraft in maintaining a programmed route to the moon was to fire the engine of the S1VB for a limited time for translunar insertion (TLI). This is done to put the spacecraft on a proper trajectory to the moon. If engine thrust was precise, it would have to put the CSM on its proper trajectory, that is, an elliptical orbit around the Earth extending to the far side of the moon. This is the free-run trajectory, which would have put the Apollo spacecraft on a course around the moon and back to the Earth in the case of a service module engine failure. It's interesting to note that the subsequent Apollo missions gave up the free-run trajectory for the hybrid trajectory. This was apparently done to save fuel, putting them on a trajectory to their respective moon landing locations. NASA considered the risk of an SM engine failure to the minimal, therefore they gave up the free-run trajectory. That would have been an enormous gamble to take in a manned mission with one engine 240,000 miles from Earth. Proponents of these missions have argued that the LM descent engine could have been used as a backup. However, the LM engine wasn't as powerful as the CSM engine, and given the flimsy design of the LM, it's quite conceivable that the structural damage would have taken place during the Saturn V launch due to atmospheric forces. There are a number of scenarios that could have seriously damaged the LM, therefore, relying on that as a backup would have required its own backup. After the S1VB fired its engine to put Apollo 11 on its trajectory to the moon, it was followed by a separation by the CSM, which would have had to use its RCS thrusters to move away from the S1VB. The CSM would then have to turn 180 degrees to move towards the S1VB to dock with the LM to extract it. The CSM, now docked with the LM, would then have needed to turn 180 degrees back to its original position for its continued trajectory towards the moon initiated by the S1VB. Complicated maneuvers like this were supposedly done by a non-autonomous computer. The astronauts would have been marooned in space. Apollo 11 CMP Michael Collins claims that the Apollo method of navigation had an accuracy of 0.01 degrees. Author Ralph Renee writes, Collins says that he was thrilled when the unit flipped up its 5 balls in praise, but this represented 0.01 degree accuracy, not an exceptional result by today's standards. There are 60 nautical miles to a degree, and 0.01 degree equals 0.6 nautical miles. Many navigators on small wave-tossed boats equal this performance. Works well in small boats and planes, but on a 480,000-mile round trip? Ralph Renee continues on with an in-depth examination of his book using an analogy. I'll use a variation of that analogy to show how easily a spacecraft moving through the vacuum of space can, for a variety of reasons, move off course. There's a method general aviation pilots use to check their track, called the 1 in 60 rule. This means that when you've traveled 60 nautical miles and are 1 degree off course, you are now 1 nautical mile off course. It's an easy situation for pilots to correct along cross-country trips, especially with map readings and references to ground terrain along with navigation equipment, that is, if you correct your track promptly. But with the Apollo missions, we're not talking about a cross-country trip. We're talking about a 480,000-mile round trip in cislunar space with little or no tracking capabilities with only the stars as a visual reference using a non-autonomous computer. Now apply a version of the 1 in 60 rule to these factors. The speed of the CSM while decreasing due to Earth's gravity until the equigravisphere neutral point and where the moon begins to exert its gravitational influence due to the Apollo spacecraft's track. The moon is on its orbit moving at a speed of 2,300 miles an hour, which traveled about 155,000 miles in its orbit around Earth as it moved into position for the planned interception by the Apollo spacecraft. The celestial method of navigation using a non-autonomous computer that required interface by the astronauts for specific programs. Also, the lack of visual references, that is, the limited options and star sightings available for navigation. Having no radio navigation equipment comparable to the technology and precision in navigating as aircraft have, and having little or no tracking capabilities of the Apollo spacecraft from mission control. These points require an autonomous computer for complex calculations. The AGC did not have this capability, so with the above points factored together, the Apollo spacecraft would have moved off course by thousands of miles for a number of reasons requiring a delta V, or change in velocity and direction, that needed to use propellant to fire the engine for putting them back on course. And because of the weight restrictions for getting into orbit, propellant was limited, so there wasn't much, if any, margin for error. The method of navigation used by the Apollo missions was to check to make sure that they were on course, not to maintain it. The AGC didn't have this capability, which was why checking for any necessary course corrections was done in the first place. This is one of the many scenarios for the limited performance that the AGC would have to deal with. If this method of navigation were used in actual conditions, this would have been a sure-shot recipe for disaster, marooning the Apollo mission astronauts in orbit in cislunar space for eternity. Tracking Apollo missions the NASA way. Now that we've established that the AGC was not capable of maintaining course, how did the astronauts know when to make course corrections? The answer is they didn't. NASA had to come up with a method for tracking the Apollo spacecraft so that they could inform them when to perform a course correction. Aircraft tracking and navigation is accomplished with ground and other onboard equipment, but on spacecraft there are limits to how much weight can be launched. Therefore, everything possible is done to keep it to minimum. For the Apollo missions, a way had to be determined to track the spacecraft since radar had a limited range, and this needed to be done without bulky equipment and excess weight. The method NASA came up with was called the Doppler effect. This was supposedly done by Mission Control in Houston, Texas. The Doppler effect is usually likened to the horn of an oncoming car, which appears to rise in pitch as it's moving toward the observer, and then appears to decline in pitch as it moves away from the observer. The actual pitch of the horn never changes. The same method is applied in radio frequencies from the Apollo spacecraft when moving away or towards Earth tracking stations. However, because of the thermal extremes of space and the excessive equipment needed on board a spacecraft to send signals of sufficient strength using this method, NASA says it found a way to use the Doppler effect without the need for this excessive equipment on the CM. Given that a powerful, accurate radio signal would in any case be sent to the spacecraft to carry voice and data from Mission Control, engineers simply arranged that it be modified on board in a known way and retransmitted back to the ground, this time carrying voice and data from the spacecraft. If the frequency of the signal from Earth was precisely known, then so was the spacecraft, if it were not moving. After equipment on the ground received the downlink from the spacecraft, the precise frequency was compared to the uplink. A lower frequency meant that the spacecraft was moving away from the ground station, and a higher frequency meant that the spacecraft was moving towards the ground station. NASA claims that this modified method could determine the CM's distance to an accuracy of about 30 meters, which avoided the need for excessive onboard equipment. The Doppler effect method. So precise that it could have been used to track the CM and allow Mission Control at Houston to radio the astronauts to make a course correction if needed, based on tiny Doppler shifts in radio frequency that determine the CM's position to an accuracy of 30 meters anywhere on a 480,000-mile round trip in cislunar space, without the necessary equipment on board the CM, relying on no disruption in radio frequency. Radio and communication failures happen all the time, even with today's more sophisticated network. However, since radar wouldn't have the range needed to track spacecraft in cislunar space back then, NASA had to come up with a method of tracking the Apollo spacecraft in a way that would at least convince the public. Yet NASA had said that this method worked perfectly for all of the 9 Apollo missions that supposedly went beyond low Earth orbit. And if it seems NASA was stretching its navigation technique a little, the Apollo 13 incident was another story altogether. Theatrics at its best. On April 13, 1970, Apollo 13 had an oxygen tank explosion in the service module while docked with the LM en route to the moon. Although technically it was an electrical fire that caused an overpressurization and rupture in oxygen tank number 2, which damaged oxygen tank number 1. However, the overpressurization was enough to blow the side panel off the service module SM. In the astronauts' heroic attempt to save their spacecraft, they abandoned their moon landing and powered down the CM to save power, which they would need for re-entry into the Earth's atmosphere. Since the CM was powered down, that meant that the AGC was powered down as well, which meant no navigation system. They had to rely instead on the LM's navigation system to get them back to Earth. But because the LM's primary guide and navigation system, the PGNS, would have used too much power, which was now limited, they instead used the backup computer, the LM's abort guidance system, AGS, to help navigate back to Earth. Meanwhile, the explosion in the Apollo 13 SM was now venting particles, which was complicating their ability to distinguish them and the star sightings needed for position fixes and course corrections. So now the astronauts are in a serious life-threatening situation in which they have to resort to using a non-autonomous backup computer with even less power and memory than that of the AGC. And while there were contingencies that included using the LM descent engine in the case of the CSM engine failure, apparently none of them included the Apollo 13 scenario. There's a possible reason for this. At the time of the Apollo accident on April 13th, 14th, 1970, this Frau Moreau site was actually a considerable distance into the unlit side of the Terminator. This is such a crucial point that we sought verification on the circumstance from Dr. Percy Seymour, astrophysicist and principal lecturer in astronomy at the University of Plymouth, England. Percy confirmed that this was in fact the case and kindly supplied us with his own computer printout illustrating the position of the Terminator at 23:30 hours GMT on April 13, 1970. Apollo 13 was inadvertently scheduled to land on the unlit side of the Terminator in an area called Frau Moreau. All of the missions were scheduled to land on the unlit side of the Terminator since their only lighting was the sun. This had been confirmed by other authors using program software called Celestia, a 3D astronomy program created by Chris Laurel. Somehow, NASA miscalculated the landing of this fictitious mission, so they needed to come up with a solution. Therefore, the Apollo 13 accident scenario was invented to rescue NASA from embarrassment. They obviously made a blunder in planning this mission that it would have landed in the dark. Proponents have countered that Apollo 13 would have landed near the Moon's Terminator on the sunlit side. However, given the close proximity to the unlit side and the fact that the astronauts were using visual landmarks searching for a suitable landing site, their approach left no margin for error. This would have been hazardous to say the least. Charts and slide rules. The Apollo mission's method was to use the AGC along with charts and slide rules. Mission Control in Houston would send information by voice to the astronauts for mid-course corrections, not digital data. This required communications and data uplinks to be 100% reliable. There is the probability factor, which usually gives a high percentage of success and reliability, but there are usually backup systems to increase that reliability. With the Apollo mission's method of navigation, there was no backup system. This contradicts the safety factor for a manned mission on a 480,000-mile round trip in cislunar space. A realistic manned mission in cislunar space would require an onboard autonomous computer with the necessary speed and memory capacity for any scenario encountered on a 480,000-mile round trip. That would require programming into the onboard computer software memory a reference frame for navigating, which was supposedly done. But as has been established, the AGC required crew interface, which would have been time-consuming and inaccurate to say the least. Realistically, the AGC would have needed an autonomous capability for solutions including constant updates by the nanosecond of the Earth and Moon's orbiting position in relation to the Sun, stars, and most importantly, the CM. And note, this would have to have been done in real time. The AGC would then use the data to update projected propellant requirements, velocity, and estimated time en route to numerous checkpoints on a continuous basis, very much like what is done in aviation. As soon as a course correction is necessary, an autonomous computer instantly finds solutions, performs the maneuver, while alerting the astronauts through digital displays. The AGC did not have this capability. The limited capacity and memory of the AGC. As mentioned earlier, the AGC required crew interface for altering, updating, or switching to another program. For added safety, the main computers at Houston would have been running the same programs for comparison. In fact, NASA claims that the mainframe computers at Houston did the most complicated or biggest part of the computations, which were then uplinked to the onboard AGC. That alone raises some serious questions as to the efficiency of the AGC and the safety of the manned mission in low Earth orbit or beyond using this limited technology. It has been said that the AGC has less computing power and memory than that of the average pocket calculator. This is true considering that the AGC had a memory capacity of 38,000 words, which is a fraction of any modern personal computer. Proponents of the Apollo missions counter this by saying that unlike today's computers, the AGC didn't have the need for running numerous other programs like displaying video. However, the average modern-day computer isn't responsible for the lives of manned missions outside of low Earth orbit in cislunar space on a 480,000-mile round trip. The information that was uploaded to the AGC, or voiced up for the astronauts to write down, relied on the uplink and the communications being 100% reliable. But even with the uplink, it still doesn't consider the need for a computer to find instant solutions to any emergencies in cislunar space. Example: an environmental system failure, or adverting possible celestial debris where even a second's delay could spell catastrophe for the crew. In a perfect world where absolutely nothing could go wrong, maybe the AGC might have been able to barely complete its task, theoretically that is, and possibly in low Earth orbit, and even that's a stretch given its purported limited memory as claimed by NASA. Computer engineer Xavier Pascal writes, "Some say that it was not important if the Apollo guidance computer was underpowered because it was the mainframe computers back on Earth that were calculating the trajectory of the Command and Service Module CSM. It is totally impossible for these computers to calculate in advance the entirety of the trajectory commands to the engines because commands to an engine are only approximate and there is always a slight margin for error. Over time, such errors accumulate and become significant. The delay in sending commands from the mainframe computer in Houston to onboard AGC is about 1.25 seconds and the same time for the signal to come back. That's a total of 2.5 seconds, which may not seem like much, but in fact it is quite long in the case of an emergency. There would have been a further time delay for Houston's mainframe computers in finding solutions to a specific problem since data was sent up by voice communications, which now translates into minutes. An emergency can spell the end of a mission in seconds. You don't have minutes waiting around for mission control back on Earth trying to figure out a problem." Xavier Pascal made comparisons of the AGC to a UNIVAC computer of the same era. Although the core memories of the two computers display similarities, they work in a very different manner, the wires passing through or bypassing the cores being sense wires in the case of the Apollo memory, these wires being activation wires instead in the memory of UNIVAC. In the case of the UNIVAC memory, each core had a unique sense wire, so there was no problem regarding the division of current in the sense wires as with the memory of Apollo. And that fact makes a whole difference between a core memory which can work and one which cannot. In fact, Pascal's conclusion regarding the AGC is startling. In short, this computer had no memory, none at all, neither ROM nor RAM. With the disk key unit which was not working correctly, the AGC definitely appears to be a complete fake. But if this Apollo guidance computer was a joke, it was because the engineers intended it to be so, and not because they were incompetent. The engineers placed incoherence absolutely everywhere. All the electronic interfaces were stuffed with intentional errors. The AGC's performance can be summarized as follows: low computing power, no memory, non-autonomous, a complete fake. Where exactly is the equigravisphere? There's one more curious anomaly, and that is regarding the equigravisphere, the point at which Earth and the Moon exert equal pull or gravity, also called the gravitational neutral point, which was necessary for the calculated neutral point CNP at the date and time of Apollo 11. After TLI, the Apollo spacecraft would have needed to be precise in reaching the CNP while factoring in its corresponding decrease in forward velocity due to a pull of Earth's gravity. At the CNP, Apollo 11 would then enter the influence of the Moon's gravity, therefore increasing forward velocity. So, the pre-calculated time in mission planning becomes vitally important, since any discrepancy would require the use of propellant, which was limited due to weight restrictions for launch. Isaac Newton calculated the equigravisphere at 215,000 miles from the Earth and 23,900 miles from the Moon for a total distance of 238,900 miles. Discrepancies in the CNP for the date and time of Apollo 11 are as follows. The Time magazine issue of July 1969 listed the CNP as 43,495 miles from the Moon. In 1981, David Baker's Space Technology lists the total distance to the Moon as 253,475 miles. He did not publish the CNP, but his total distance between the Earth and the Moon differs from that of Isaac Newton. David Baker was involved in the Apollo 13 mission. Space Travel, a History. An update of history of rocket and space travel by Wernher von Braun, Frederick I III Ordey, and Fred Durant lists the CNP as 43,495 miles from the Moon. This corresponds to the Time magazine figures. Spaceflight and Technology, a chronology by David Baker, published in 1996, puts the CNP at 38,925 miles from the Moon and 214,550 miles from the Earth, for a total distance of 253,475 miles. This total distance corresponds to his 1981 publication, but this time he has published the CNP. The First Men on the Moon, The Story of Apollo 11 by David M. Hardland, puts the CNP at 33,822 nautical miles from the Moon and 186,437 nautical miles from the Earth, for a total distance of 220,259 nautical miles. When these figures are converted from nautical miles to statute miles, David Baker and David M. Hardland's numbers come close, but there's still a discrepancy of several miles. For a manned mission to safely travel to and from the Moon with limited propellant on board, precise calculations are imperative. Simply put, there cannot be more than one distance between the Earth and Moon on the same date and time, and there should only be one figure for distance from a given planetary body at which the calculated neutral point, CNP, occurs. Aside from the obvious propellant required to compensate for any errors in calculation for the CNP, how would they have even known that they had reached the CNP sooner or later than expected? The AGC would not have had the capability for detecting this. Therefore, given the discrepancies in the figures above, this is another scenario in which the astronauts could have found themselves marooned for eternity in cislunar space. NASA has never explained this discrepancy. Redundancy, hand and eye coordination. As for redundancy in the case of an AGC failure, and unlike Apollo 13 without the ELM or its onboard PGNS or AGS on its route back to Earth, NASA says that the command module had a second control system that could operate independent of the other systems, called the Stabilization and Control System, SCS. This stabilization and control system, SCS, could maintain altitude and allow the crew to make accurate maneuvers and, if necessary, even manually control the SPS engine. In other words, NASA says that if necessary, the astronauts could have hand-flown the CSM 240,000 miles back to Earth with nothing more than hand and eye coordination. Chapter 4. Radiation belts and the Earth, intense solar storms, and galactic cosmic rays. To glow or no glow? The Apollo missions would have had to travel through an area of radiation surrounding the Earth called the Van Allen belts. This is an area of intense radiation, and there has not been much discussion over the years regarding NASA's claim that, given the right shielding and trajectory, the Apollo missions were able to travel through the radiation belts with little or no harm to the astronauts. However, when one actually goes through the literature regarding the Van Allen belts, conflicting pieces of information become apparent. Today, NASA admits that there are many problems that need to be solved before sending manned missions through the Van Allen belt, which will be discussed in detail in this chapter. However, the subject and background radiation on Earth and in space is a very complex one, and when it comes to the latter, designing protective shielding for spacecraft isn't as straightforward as it is often presented in the media. Then there's the danger of micrometeoroids and thermal control that needs to be factored into the spacecraft shielding design as well. In this chapter, we'll focus on the dangerous radiation environment, which presents a constant threat to any manned space mission, including the area of space beyond low Earth orbit, LEO, and outside of the Earth's magnetic field. To completely block radiation in the space environment, the spacecraft requires shielding of different materials, for example, lead or enormous amounts of water. Due to the excess weight of these materials, a launch would be a near impossibility with the technology available today. Therefore, spacecraft shielding is designed to decrease the intensity of radiation to acceptable limits for the astronauts using materials that minimize weight for launches. This is what's called attenuation of radiation. It is the claims made by NASA when discussing attenuation of radiation that we'll focus on. Spacecraft shielding that would actually be needed for radiation in space and low Earth orbit and beyond, as well as for protection of micrometeoroids and thermal control, we'll be discussing in Chapter 5. Factors to consider in the attenuation of radiation and accumulated doses include 1. The overall health of astronauts, 2. Gender and age, 3. Number of previous manned missions they may have been on, and 4. The duration of any specific manned mission that they may be considered for. For example, a particular astronaut's previous mission or missions, depending on the duration of exposure to radiation, may disqualify him for any future mission. It would take many books to talk about the history and theory of radiation and its effects on people, more specifically astronauts in the space environment. However, for most of us, myself included, a brief review of some of the basics of this subject will help in appreciating the complexity involved, which I have provided in this section. Basic theory. There are 3 sources of radiation in space. 1. High radiation particles around the Earth trapped by the magnetosphere are called the Van Allen belts. 2. Solar storms which originate from the Sun, which are referred to in several ways. For example, solar cosmic ray events, solar proton events, solar energetic particle events, energetic storm particle events, ground level events, proton showers, and solar cap absorption events, or as is commonly referred to as solar particle events, SPEs. Also, there are coronal mass ejections, CMEs, which are associated with SPEs. From here on in, we'll refer to the terms SPEs and CMEs. 3. Galactic cosmic rays, GCRs, which come from the Sun and from all directions outside of the solar system. Guidelines most commonly used for reference are from the International Commission of Radiological Protection, ICRP, and the International Commission of Radiation Units and Measurements, ICRU. Basic measurement units are used as a reference point in an effort to appreciate and understand some of the challenges for spacecraft shielding and the attenuation of radiation. For more detailed information, you can refer to the ICRP and ICRU. There are 4 aspects of radiation to consider. There are 2 types of radiation, ionizing and non-ionizing. Examples of ionizing radiation include alpha particles, beta particles, X-rays, and gamma rays, all of which are harmful and measured as an absorbed dose by the unit joule per kilogram (JkG). In physics, 1 joule per kilogram is called a gray (GY). Outside of the Earth's atmosphere, astronauts need protection from ionizing radiation in low Earth orbit and beyond. This becomes even more important for astronauts as they venture beyond low Earth orbit and Earth's protective magnetic field. B. Equivalent dose. Since there are different types of radiation, there needs to be a further method of determining its biological effects. Proponents of the Apollo missions say that alpha radiation in the outer regions of the Van Allen belts can easily be stopped with a few centimeters of air or paper, while beta radiation can be stopped with aluminum, thus giving the impression that manned missions through this region would cause little or no harm to the astronauts as long as they traveled through this area quickly. This is partially correct. However, as this chapter will show, NASA is not sure of the energy levels in this region of space around the Earth, and if alpha particles are inhaled or ingested, they could be the most destructive form of ionizing radiation, given that alpha and beta radiation will have different biological effects. A numerical quality factor Q between 1 and 20 is used to determine the equivalent dose. Alpha particles are given a Q factor of 20 since it causes more harmful biological effects once ingested. Beta and gamma radiation are assigned a Q factor of 1. Alpha and beta are forms of particle radiation that are relatively easy to stop. Even though gamma radiation is assigned the lowest Q factor, it can be the most penetrating, causing enormous harm to astronauts depending on its energy. Therefore, 1 GY of alpha radiation is 20 times more harmful than 1 GY of beta or gamma radiation. The sievert, SV, which is the International Unit System, SI, is used to interpret the varying biological effects from different types of radiation. For reference purposes, 1 GY of alpha radiation is an equivalent dose of 20 SV. 1 GY of beta radiation is an equivalent dose of 1 SV. 1 GY of gamma radiation is an equivalent dose of 1 SV. Other types of radiation are given different Q factors between 1 and 20. Effective dose. Since different types of radiation can strike different parts of the body, a new quantity called the effective dose is used in which each organ or part of the body is assigned its own Q factor. This is one of many factors considered when designing spacecraft shielding. The figures used above and equivalent dose are further broken down into millisieverts, MSV, or 1 sievert is equal to 1000 millisieverts. It is the millisievert that is usually used in determining the effective dose for individuals. And when using figures such as 0.1 millisieverts or 1 sievert, you still use the Q factors 1 to 20 to multiply them. Dose rate. A dosimeter is used to measure the dose rate, usually in millisieverts per hour. The Apollo astronauts were supposed to have carried a dosimeter on board. Although average dose rates for the Apollo astronauts have been released, individual dose rates remain classified. The RAD and the REM. The absorbed dose was referred to as the RAD, while the equivalent dose was referred to as the REM. Thus, these are old terms which now have been replaced by the GY-NSV. The average yearly dose per person in background and man-made radiation in the United States is approximately 0.62 rems, which is 620 mrems, or as expressed in the new unit, 0.0062 sieverts, or 6.2 millisieverts. Many of the science and engineering books I've referred to have used the old term of rems. I'll refer to this term and use 0.62 rems as the approximate average per person yearly dose in the United States as a reference point when discussing attenuation of radiation and how many rems astronauts could have been exposed to. There are many online conversion tables that can be used to convert rems to sieverts if necessary. I hope this brief description will help you in your research into the Apollo moon missions when reading about shielding and attenuation of radiation, which will be discussed further. Van Allen radiation belts. The Van Allen radiation belts are two regions of energetic particles that encircle the Earth, excluding the north and south polar regions. Any manned mission to the moon would have required a trajectory through the radiation belts, which NASA claims is safe for astronauts as long as they have proper shielding as they travel through the outer regions of the outer radiation belt quickly, therefore minimizing radiation exposure. Discovery of the Van Allen belts. In 1958, Dr. James Van Allen discovered two radiation belts surrounding the Earth through two unmanned missions. Explorer 1 launched February 1, 1958, and Explorer 3 launched March 26, 1958. The inner and outer radiation belts consist of energetic charged particles, the inner belt consisting predominantly of protons and the outer belt of electrons. Dr. James Van Allen writes, "The inner belt reaches its peak at about 2,000 miles from the Earth, the outer one at about 10,000 miles. Beyond 10,000 miles, the radiation intensely diminishes steadily. It disappears almost completely beyond 40,000 miles. The maximum intensity of radiation in each belt is about 25,000 counts per second, equivalent to some 40,000 particles per square centimeter per second. The maximum intensity of radiation in each belt is about 25,000 counts per second, equivalent to some 40,000 particles per square centimeter per second. Solar wind is tenuous ionized gas called plasma and is the main source of energetic charged particles in the radiation belts. The solar wind, or ionized gas, encounters the Earth's magnetic field by first hitting the magnetosheath, which is often referred to as the bow shock. This area extends approximately 37,000 miles from Earth. Below the magnetosheath is the magnetopause, and below that is the magnetosphere. From here, these charged particles in the magnetosphere, mainly protons and electrons, are trapped inside Earth's magnetic field. Within Earth's magnetic field, these charged particles are now influenced by Earth's magnetic north and south poles, traveling along magnetic field lines. Hence, the Van Allen belts are in constant flux and form one of the many pertinent factors to consider when sending manned missions through this area. Conflicting information regarding intensity of Van Allen belts. People who question the Apollo missions are usually referred to as conspiracy theorists. This term was invented by the CIA to dispel any rumors of conspiracy regarding the JFK assassination. Further, conspiracy theorists are often accused of quote mining. It is another term used in an attempt to further discredit anyone writing about this subject. Quotes are used by authors at the time, and I will use them in this chapter to show the discrepancies and conflicting information regarding the Van Allen belts. We'll start with the conflicting information regarding the size and energy levels of the radiation belts, as is presented in numerous books and articles. Here are several points taken from 6 sources that show the discrepancies and conflicting information regarding the Van Allen belts. After each source, I offer my analysis. 1. Dark Moon and the Whistleblowers by Mary Bennett and David S. Percy. In Spaceflight and Rocketry, a chronology, David Baker has an entry dated March 20th, 1959 for an announcement of further radiation belt data from Professor James Van Allen, stating that the inner belt extended from 1,500 to 3,000 miles, the upper belt from 8,000 to 55,000 miles. Yet the same year, in the highly respected Scientific American, James Van Allen states that the radiation zones extend to 64,000 miles. In 1997, websites quoted the starting point of the Van Allen belt at between 250 and 750 miles from Earth, hardly a starting point and more of a vague zone. Also in 1997, British university students were also informed that the Van Allen belts extended from 621 to 3,107 miles for the lower belt, and the upper belt only continues to a mere 12,430 miles. The above distance is even more astonishing, with the upper belt apparently ending 51,570 miles short of Van Allen's own data. As this list compiled by Bennett and Percy shows, there are several different interpretations of the data. It would provide some clarifications if the scientific community could at least agree on where the radiation belts start and where they finish, considering the solar wind that extends the Earth's magnetic field on the side away from the Sun. In any manned space mission, an absence of precise data as to the extent of the radiation belts means that an exact length of time which is safe for astronauts to be exposed to radiation can't be determined. Radiation and the International Space Station recommendations to reduce risk by Space Studies Board, Board of Atmospheric Sciences and Climate, National Research Council says, one component of the belts, the outer belt MEV electrons, has long been known to be highly variable. Flux frequencies vary by several orders of magnitude, with an interval of high flux observed typically once a month. Though MEV electrons rarely penetrate into the interior of a spacecraft, they can be hazardous to astronauts performing EVAs. Most other components of the belts, including highly penetrating energetic protons, are generally much more stable and predictable. However, we now know that stability is not absolute. The actual data for outer electron flux is not defined in their text. Does this mean that there's a possibility that several orders of magnitude of MEV electrons have the potential of penetrating a spacecraft shielding, posing a risk to astronauts? Yes, it does, and their quote, MEV electrons rarely penetrate into the interior of spacecraft means that they penetrate given the magnitude of the flux. The information from the second source above is a contradiction in terms and particularly significant as it will be seen next. Space Radiation Hazards and the Vision of Space Exploration report of a workshop by National Research Council of the National Academies. The region of trapped radiation within Earth's magnetosphere consists of energetic protons, electrons, and heavy ions organized in two belts, a relatively stable proton-dominated inner belt and a highly variable electron-dominated outer belt. Energies range from approximately 10 keV to greater than 400 MeV for protons and from tens of keVs to greater than 10 MeVs for electrons. Manned missions in geospace are flown in low Earth orbit at altitudes below the inner belt. However, astronauts embarking or returning from journeys to the Moon or Mars will have to pass through the Van Allen belts and will be exposed for brief periods of high levels of radiation. We just learned from the National Research Council's previous quote from Source 2 that the inner proton belt stability is not absolute. Yet, in the quote just above from Source 3, they're now saying that the inner proton belt is relatively stable, therefore insinuating that it's now absolute. This is a major contradiction. It would also help to know what the intensity of these high levels of radiation are, as they would have to have been determined during the Apollo missions 50 years ago. But decades later, they are now questioning radiation intensity in this region. So, either NASA has lost this data, or they never had it to begin with. How Apollo Flew to the Moon by David W. Woods. For a few minutes, as they raced away at 10 kilometers per second, the crew passed through the Van Allen belts where they received a small dose of radiation. This is an inner torus populated by energetic protons which the spacecraft passed through in a matter of minutes and against which the spacecraft's skin was an effective shield. The spacecraft took about an hour and a half to traverse the more extensive outer torus, but this region has mainly low energy electrons and so was less of a worry to mission planners. Notice how W. David Woods quickly skims over the issue of attenuation of radiation with his phrase, "The spacecraft's skin was an effective shield." This quote also represents more conflicting information regarding how long each Apollo mission would have taken to travel through the Van Allen belts. As to how long the Apollo missions were in their radiation belts depends on the source, as I have read several estimates, none of which seem to agree. The graph below shows different estimates by varying groups as to how long the Apollo missions were in these regions of the Van Allen belts. On a matter as important as this, all sources should agree, and as is evident, they don't. Dr. James Van Allen in Scientific America, March 1959. Unless some practical way can be found to shield space travelers against the effects of radiation, manned space rockets can best take off through the radiation-free zone over the poles. This is interesting since the discoverer of the radiation belts, Dr. James Van Allen, has said that manned missions should travel in an area through the north or south poles, which there is little or no radiation. Near the end of this chapter, you'll see why it took Dr. Van Allen over 30 years to refute his own statement about manned missions safely traveling through outer regions of the Van Allen belts besides the radiation-free zones. An Introduction to Space Travel by Mark Moldwin. The radiation belts contain intense radiation that can kill astronauts and damage or destroy sensitive electronics on spacecraft. Understanding this region is one of the main efforts of space weather, since many important satellites have their jobs in or through the radiation belts. NASA recently posted a YouTube video with one of its engineers, Kelly Smith, talking about the intensity of the radiation belts and the need to solve numerous problems before sending manned missions through them. Proponents say that the intensity of the radiation belts Kelly Smith is talking about only applies to sensitive modern electronic equipment on board new spacecraft. Mark Moldwin's above quote shows that's partially true, but radiation intense enough to harm sensitive electronic can also harm or kill the astronauts. Smith completely ignores the Apollo missions' travel through the outer regions of the radiation belts, and he doesn't specifically say in the video where those radiation intensities are. Hence, the inference is, it's not safe for manned missions no matter what area of the radiation belts these missions attempt to go through, and that's with 21st century technology. Note, with the exception of Dr. James Van Allen, all above quotes come from sources decades after the Apollo missions. There's one more thing to add here, and that's the variation in the Earth's magnetic field over the South Atlantic. It's the area of the Van Allen belts that dips to an approximate altitude of 100 miles over Brazil and stretches out over the South Atlantic Ocean, commonly referred to as the South Atlantic Anomaly, SAA. Special precautions aboard the International Space Station, ISS, need to be taken whenever traveling through this region because of intense proton radiation, while on the other hand, all Apollo manned missions spent 10 to 15 minutes traveling through this inner belt with no apparent health effects on the astronauts. This presents more conflicting information from NASA. Outer electron belt would have exceeded Apollo spacecraft shielding. In this section, we'll use the terms KeV, MeV, and GeV. KeV, kilo electron volt, which is 1000 electron volts, MeV, mega electron volt, which is 1 million electron volts, and GeV, giga electron volt, which is 1 billion electron volts. A reference point to remember for the Apollo missions is that the attenuation of radiation up to 14.7 MeV electrons in the predominantly electron outer Van Allen belt. Being exposed to high levels of radiation for short periods of time is tolerable, but of course, you want to know what the energy flux of these high levels of radiation are. The Proton AP and Electron AE8 radiation belt models of 1976 say that electron energies are no greater than 7 MeV in the outer Van Allen belt. Yet, as was mentioned above, the National Research Council published its report in 2006 and said electron energies are greater than 10 MeV. However, in their 2008 publication, the National Research Council refers back to the AP8 and AE8 models of 1976. It states, the trapped particle models in current use are the AP8 for protons and the AE8 for electrons, Sawyer and Vette, 1976. Although the AP8 and AE8 models are still widely used for spacecraft design, it is recognized that they are severely outdated because of the secular changes in Earth's magnetic field since the era when measurements underlying the models were made. It is now recognized that radiation belts vary on timescales shorter than just the solar maximum, solar minimum levels described in the AP8, AE8 models. Example, Blake ETAL 1992, LIETAL 1993. NASA's Living with the Star program's radiation belt storm probes, which are scheduled for launch in 2012, are expected to provide measurements that will be the basis for new models. In the meantime, there are also efforts aimed at extending the capabilities of existing models and improving their accuracy through reanalysis of existing datasets. Beta version of new models, designated AP9 and AE9, are scheduled for release in 2009 to 2010 timeframe. Efforts at improving models for Earth's trapped radiation are important for other NASA missions, as well as the DoD and for commercial use of space. Now we're back to the Van Allen belts with electrons no greater than 7 MeV. So which is it? 7 MeV electrons or greater than 10 MeV electrons? Since the National Research Council says that there are electrons greater than 10 MeVs, how high do these electron energy fluxes go? This is the most important question of all, since NASA claims the Apollo spacecraft shielding can stop electrons up to 14.7 MeVs, the reference point mentioned above. The 1976 AP8, AE8 radiation belt models have been used by proponents of the Apollo missions in an attempt to prove that the Van Allen belts were safe for manned missions to travel through using the method NASA claimed. Decades ago, NASA was confident in its technology to send manned missions through the Van Allen belts. However, it now seems that NASA and scientists in general are more perplexed about the Van Allen belts than ever before. This is disturbing since spacecraft shielding design based on the AP8 and AE8 models, which now conflicts with the National Research Council's estimates. And with the new AP9 and AE9 models, NASA still doesn't know how high the electron energy fluxes are, which is discussed in detail next. Clash of the Titans. A well-known Australian researcher by the name of Gerard White has been questioning the validity of the Apollo missions for years through his excellent videos, which you'll find on his YouTube channel. He has raised some very interesting but disturbing questions about the Apollo missions that NASA refuses to answer. However, NASA is not without its defenders. One of these defenders is Robert A. Browning, who got into a very interesting and revealing, albeit indirect, online discussion with Gerard White. Browning published an online article in which he attempts to counter conspiracy theorists regarding claims that the Van Allen belts are harmful to any manned mission attempting to travel through them, including the outer Van Allen belt. Note: Browning claims to be a civil engineer and an average person fascinated by rocketry and spaceflight. You can research his article online by typing his name in along with Van Allen belts, and you can check out his other work at www.browning.us. Browning in his article shows the actual supposed trajectory through the outer regions of the outer radiation belt. Using mathematics, he explains that given the right method of spacecraft shielding, as is claimed by NASA, the Apollo missions could have safely traveled through the outer regions of this belt. His basis for this data is the 1976 AP8 AE8 model of the Van Allen belts. When you read through all of the mathematics, you realize that he's using estimates to formulate his own theoretical model. There is no real-time data for the Apollo missions in Browning's article regarding the regions of the outer Van Allen belts, which we'll soon see. His data conflicts with that of the other scientists involved in researching the Van Allen belts. Gerard White counters Browning's online paper with his own use of mathematics, although it is a source of his data that is most interesting. In his YouTube video, Radiation Reloaded, White discusses the data regarding the Van Allen belts, focusing on the trajectory of the Apollo missions. 24 minutes into the video, he specifically counters Browning's claims that White's previous YouTube video, he had used erroneous data to prove that the outer Van Allen belt would have been dangerous for any manned mission. While Gerard White was researching for a university assignment, he came upon a credible source. In an article by Herbert O. Funston and his team from the Los Alamos National Laboratory published on March the 8th, 2013, Funston talks about penetrating radiation, saying electron fluxes are typically observed at energies greater than 15 MeV in both radiation belts, with inner belt proton energies that can exceed 100 MeV. According to the published reports by the National Research Council in the year 2000 to 2008, energies greater than 30 MeV protons can penetrate the mid-deck of the Soviet shuttle. Hence, one should assume that the Apollo spacecraft would be no different. This is interesting considering NASA's claims that the Apollo spacecraft shielding was enough to stop up to 14.7 MeV electrons. White contacted Funston and asked him to quantify the fluxes of the electrons. Funston referred White to one of the authors of the article, a space physicist, Dr. Jeffrey D. Reeves. In his correspondence with White, Reeves, a world expert on the subject, made a startling statement. I've reproduced it here in its entirety from Gerald White's YouTube video, Radiation Reloaded, to avoid misrepresentation. Dr. Jeffrey D. Reeves, the answer is we don't know. Most places in the magnetosphere, there are no electrons with energies greater than 1 MeV. They just don't stick around long enough. In the inner magnetosphere, they can be trapped for a long time. Trapping in the inner belt is much longer than trapping in the outer belt, so the fluxes greater than 10 MeV electrons tend to be higher and steadier in the inner belt. How high and how steady, I'm not sure. Here's why. 1. You need a really large detector to measure greater than 15 mega-electron volts. Larger means heavier, so we typically don't fly detectors that are massive. The measurements we do have are typically inferred from backgrounds in detectors that are intended for other purposes and for which the electron response sensitivity is not well known. 2. Integral measurements like Van Allen's Geiger tubes can tell you the total counting vote of electrons that trigger a response in the detector, but the sensitivity as a function of energy is not well known. It's an integral measurement, but for some point, the sensitivity falls off. For instance, when an electron passes through a detector, it will only deposit part of its energy. 3. Bremsstrahlung. Any material around the detector will produce X-rays when hit by very energetic electrons. Those X-rays will often also be measured by the detector. But now the collecting area you assume isn't the entrance to the detector, it's the whole spacecraft. It is for these reasons that the AE-8 only goes to 7 MeV. You will either have to extrapolate the spectrum and integrate it numerically, or you will have to dig into the original literature and look into both measurements and the caveats. I'm sorry, I just can't give you the answer. For the purpose of our study, designing a detector that properly measures greater than 50 keV and ions in the region where greater than 15 MeV electrons are present, it was sufficient to know that they can be a problem. We didn't need to know the exact fluxes. The Van Allen probe satellites have an instrument called REPT that may provide the measurements we need, but it's still going to take a lot of work to extract the correct values given the problems I just outlined above. Dr. Jeffrey Reeves specifically says that the reason the 1976 AE radiation belt model goes to 7 MeV is because they didn't have the capability to detect anything higher. This confirms that NASA has no way of knowing the electron energy fluxes of the area of the Van Allen radiation belt traversed by the Apollo missions, and as Reeves also pointed out, it's still going to take a lot of work to extract the correct values given the problems I outlined above. Another problem he mentions is Bremsstrahlung. As common sense would dictate, if spacecraft shielding is not enough to attenuate radiation to acceptable levels for the astronauts, then it follows that the Apollo astronauts would have been exposed to higher levels of radiation. However, on the flip side, too much metal shielding can produce X-rays which are just as harmful to astronauts, therefore also leading to an increase in the radiation count. The only way then to attenuate radiation levels to acceptable limits for the astronauts would be to have real-time data on the radiation belts on a consistent basis and then design spacecraft shielding accordingly, or more realistically, avoid these areas altogether. NASA did not have this real-time capability for collecting data on the radiation belts. As Gerald White points out, Browning tries to get as much mileage out of the 1976 AP-8 AE-8 radiation belt models as possible. Browning goes on to say that 0.1 MeV to 3 MeV electrons represents 99.95 of the outer electron belt along Apollo 11's trajectory, and that for all practical purposes, electrons greater than or equal to 6 MeV do not exist. As Browning says, according to credible sources, there are virtually no electrons above 14.7 MeV, which is convenient for his narrative since the claim is that the Apollo shielding can attenuate electrons up to 14.7 MeV. Who exactly are Browning's credible sources? 3, maybe 4 radiation belts. In the 1950s, the United States had launched into space a series of 3 nuclear warheads under the code name Operation Argus and detonated them below the Van Allen belts. The first warhead was launched August 27, 1958 to an altitude of 110 miles. The second warhead was launched August 30, 1958 to an altitude of 190 miles. And the third warhead was launched September 6, 1958 to an altitude of 493 miles. Each warhead had a yield of 1.5 kilotons and they were detonated over the South Atlantic Ocean. The kiloton yield in these warheads may not have been considered significant, yet it was determined that the X-rays from these explosions could penetrate spacecraft and disable electronics as well as cause radio noise. To make matters worse, this area includes the SAA, where the more intense inner proton belt dips to an approximate altitude of 100 miles. It was reported that after the detonation of these warheads, the Earth's ionosphere was temporarily disrupted. There were magnetic storms and disruptions in shortwave radio communication, and additional electrons were trapped in the magnetosphere, forming an artificial radiation belt comparable to the Van Allen belts in intensity. Sir Bernard Lovell, an English physicist and radio astronomer, was particularly concerned and said, regarding Operation Argus, that the scientists' results were somewhat alarming. So now, there are 3 radiation belts. NASA doesn't say exactly when this artificial radiation belt dissipated, but confirms that during the manned Mercury missions it no longer existed. However, it can be inferred that it took at least 3 years for this radiation belt to disappear. However, by 1961, they were back to 2 radiation belts. There was also the launch of Operation Starfish Prime, another nuclear warhead. This was particularly troubling since this time they used a megaton bomb. This detonation was at least 1,000 times more powerful than the Argus bombs. It was launched July 8, 1962 and detonated 19 miles from Johnson Island in the Pacific Ocean at an altitude of 248 miles. On August 20, 1962, the Atomic Energy Commission, the Department of Defense, and NASA issued a report stating, "The solar cells of several satellites have been damaged. Measurements made in Peru calculated that the rate of radiant decay would be slow and 10% of the radio noise would still be present in 2 years' time. More than 100 trillion electrons from the fission product had been trapped by the Earth's magnetic field, which formed a new radiation belt at an altitude of 2,484 miles, with intensity over 100 times greater than the naturally existing radiation belts. The newly formed radiation belt was 400 miles wide and 4,000 miles deep, with a possible half-life of 20 years. Bennett and Percy write, "The length of a half-life is of paramount importance, as Professor John Davidson pointed out. Essentially, it continuously slows down, which means that the artificially induced radiation created by Starfish Prime would be dropped to half of its original quantity by 1982, by a quarter by 2002, to 1/8 by 2022, and that even by 2042 we would still be at 1/16 of the original amount of radiation. As the original dose was measured at 100 times in excess of the natural radiation levels, this means that by the end of this millennium, this artificial belt still contains a level that is descending from between 50 to 25 times the already intense background levels of the region of the Van Allen belts." NASA says the artificial radiation belt caused by Operation Argus dissipated by 1961. That gives the impression that there were only 2 radiation belts during the Mercury missions, but the Mercury missions took place before and after Operation Starfish Prime, so there were actually 3 radiation belts during the Mercury missions, and although the artificial radiation belt caused by Operation Starfish Prime was at a higher altitude, there would have been no way of knowing the effect of any energy flux for that whole region. Furthermore, it took until 1982 for levels to drop to half its quantity, and the Apollo missions are said to have taken place between 1969 and 1972. Then, in 2012, NASA says it discovered a 3rd radiation belt surrounding the Earth. Shouldn't it be a 4th radiation belt? NASA claims that although this 3rd radiation belt dissipated months later, they can only speculate as to what caused it. The prevailing theory is that this 3rd radiation belt was most likely caused by a solar particle event, SPE. The question is, if NASA's theory is that the 3rd radiation belt can form during an SPE, then how long would that 3rd radiation belt have been there? 1, 2, 3, or 4 months? Or instead of months, is it years? After all, NASA insinuated that it took 3 years for the artificially formed radiation belt caused by Operation Argus to dissipate. However, as has been established, the artificially formed radiation belt caused by Operation Starfish Prime is still there. This means that all of the Apollo missions would have had to travel through 3 or more radiation belts, the inner Van Allen belt, the outer Van Allen belt, and at least one artificial radiation belt formed by Operation Starfish Prime. As pointed out, by the end of the 20th century, levels of radiation in the artificial belt caused by Operation Starfish Prime would have been between 50 to 25 times the already intense background levels for that region of the Van Allen belts. When this artificial radiation belt is factored in, all of the astronauts of the Apollo missions would have had been exposed longer to extremely high levels of radiation than was reported, preventing any safe passage for manned missions through the Van Allen belts regardless of NASA's claims. There have been numerous SPEs over the decades, so the exact number of radiation belts has yet to be determined. The 2012 discovery of a third radiation belt raises an interesting point. NASA speculates that this third radiation belt was formed by an SPE. If NASA is right, then it's reasonable to assume that a radiation belt was formed by the SPE event of August 4th, 1972, which was 4 months before the Apollo 17 mission. Also, what about the intensity of this third radiation belt formed by August 4th, 1972 SPE? It's already been established that electron fluxes are typically observed at energies greater than 15 MeVs, which exceeds the Apollo spacecraft shielding. And how would NASA have even known about the formation of another radiation belt back in 1972? There's nothing in the literature back then to suggest that NASA even considered the possibility of a radiation belt forming from an SPE, which is a proven fact by NASA's own statement, which is discussed at the end of this chapter. However, it is reasonable to assume that the Apollo 17 would have traveled through 4 radiation belts and have been exposed to radiation longer than any other Apollo missions. As for Operation Starfish Prime, Sir Bernard Lovell called the effects cataclysmic. Solar particle events. Solar particle events, SPEs, can penetrate spacecraft shielding, and the best protection is to avoid them. As we'll learn in this section, SPEs have varying degrees of intensity depending on the source. As SPEs are an evolving science, they are and have always been difficult to predict. As with the Van Allen belts, we encounter a subject rife with discrepancies and conflicting information. Accelerated SPE particles are surrounded by plasma and fields that can produce electromagnetic emissions from microwaves to gamma rays. They can accelerate electrons up to 10 MeV and protons up to and greater than 100 MeV. As quoted by the National Research Council, protons comprise 90% of the energetic ions produced in an SPE, and as mentioned, protons above 30 MeV can penetrate the mid-deck of the space shuttle. This is a very serious situation for any manned mission to be caught in this solar event. Given that SPEs can arrive on Earth within minutes, there would be little to no time for any manned mission to prepare for one. As for preparing for an SPE, the only solution would be to seek the relative safety of LEO, which would put any manned mission below the Van Allen belts and well within Earth's magnetic field, which would offer some protection. But seeking the protection of Earth's magnetic field would require getting there quickly from cislunar space. Given the propulsion systems used in spacecraft during the Apollo era and today, getting there quickly would be an impossible task. Another solution was to turn the CSM around, hoping the service module will take the brunt of the SPE, which was supposed to have been one of the procedures for any encounter. Either way, you have a doomed mission. SPEs are classified as A, B, C, M, and X, with A being the smallest. Solar flares are often associated with magnetic storms, that is, CMEs. The National Oceanic and Atmospheric Administration, NOAA, further classifies these storms into 3 categories. 1. Geomagnetic storms from G1, G2, G3, G4, and G5. 2. Solar radiation storms from S1, S2, S3, S4, and S5. And 3. Radio disturbances, blackouts from R1, R2, R3, R4, and R5. Each category number means minor, moderate, strong, severe, and extreme, respectively. On January the 20th, 2005, NOAA issued an advisory for a Category 3, a solar radiation storm. This advisory warned that this specific storm had an influx of high-energy protons of greater than 100 MeVs. The advisory went on to say that a rare ground-level event, GLE, was observed. GLEs are an increase of ground-level neutrons and are associated with high-energy protons greater than 500 MeVs. It seems NASA may be holding back information about the August 4th, 1972 SPE. Maximum SPE activity during Apollo missions. Bennett and Percy Wright. The named Apollo astronauts are, however, a remarkable healthy bunch considering that during 9 alleged trips to the Moon, 1,506 solar flares were recorded, an average of 16.92 per day per mission. J.A. McKinnon, NOAA expert on solar flares, states that 10 to 20% of solar flares could be considered a medium X-ray emitter event and 1%, the deadliest of all, a Class X event. So these astronauts should have encountered 16 to 33 Class M events and at least one Class X event on each mission. As NASA admits, the Apollo missions took place during solar maximum when large SPEs were expected to occur. With the above quote, the National Research Council reiterates the point regarding solar maximum. Either it didn't occur to them that the Apollo missions were in potential danger outside of the protective shielding of Earth's magnetic field, or they mentioned it without explaining, hoping people would not question the insanity of such a momentous decision sending manned missions beyond LEO. The National Research Council. The problem is serious. Over the past 20 years, radiation effects have caused between 1 and 2 satellites per year, on average, to suffer a total or partial mission loss. Satellites at low altitudes in Earth orbit, LEO, stay relatively safe by ducking the intense part of the radiation belts higher up. But at higher altitudes and higher altitudes, where Earth's radiation belts reside and radiation from solar storms invades, radiation hazards cannot be ignored. The above quote also applies to satellites owned by corporations who don't even bother to report problems after an SPE, since there's no regulation that says they have to do so. Hence, the real number of satellites that are affected by solar storms, aka SPEs, is obviously higher. There are people who will point out that there are very few interruptions in communications and internet services, inferring that satellites function well regardless of SPEs. However, it should be noted that communications and internet services are primarily facilitated by underground and underwater fiber optic cables. The National Research Council. It delivered a total dose of radiation over half a day that, had it missed the middle or hit the Apollo missions at either end, would have caused the crew in the lunar module to suffer acute radiation sickness and, given the uncertainty in the estimate, probably even death. This is regarding the SPE of August 4th, 1972, 4 months before Apollo 17. This was the largest solar storm ever recorded in the 20th century. NASA says this storm was about 400 rem, yet according to Dr. Percival McCormick, the manager of operational medicine in the Life Sciences Division of NASA, says it would have delivered 960 rems without shielding. If the Apollo astronauts were in the LEM when this had happened, it would have been akin to having little or no radiation shielding, and the command module wouldn't have been much better. As we've established, approximately 0.6 rems is the yearly average dose per person, so with a dose of 960 rems over a short period of time, none of the Apollo astronauts would have survived, or at the very least, they would have been quite incapacitated. The figure of 960 rems is what is mentioned in NASA's reports, and given that we've learned so far, this figure is most likely higher, as SPEs have known to be in the more energetic gigavolt or GeV range. Hence, if any of the Apollo missions had been caught in this SPE, their demise would have been instant. SPEs are unpredictable. SPEs are unpredictable and dangerous to any manned missions outside of the LEO, and experts can't always explain the mechanisms of SPEs, since it is an evolving science, as they themselves admit. Given the unpredictability of SPEs, it stretches credulity that NASA would even take a chance of sending manned missions to the Moon after the solar event of August 4th, 1972, which, as previously mentioned, they are supposed to have done with Apollo 17. And that's just one SPE that we've talked about. According to the NOAA, there were 489 SPEs in July of 1969, the same month of the Apollo 11 mission. Also note that in the same year, NOAA or NOAA recorded 7,153 SPEs. The National Research Council, a solar flare and radio burst occurred during the Apollo 12 mission, which had exercised the operational procedures. The National Research Council had an opportunity to explain what Apollo 12's operational procedures were, but failed to do so. In fact, their 3 published reports from 2000 to 2008, there is a total of 1.5 pages of data from the Apollo missions, and at best, that information is scant. Bennett and Percy write, their mission occupied 14.6% of the overall Apollo profile of 89 days, and an average of 268 solar flares recorded during that time was 17.7 of the total number of flares that actually occurred during the Apollo period. Considering the inability of the agency to clad its craft against lethal radiation, and with figures like these, how long could each astronaut actually have spent on the surface of the moon exposed to lethal radiation is fairly academic. This quote is regarding Apollo 15, which experienced the greater number of SPEs and apparently the greatest avoidance of them. More conflicting information. NASA says that in the event of an SPE, the shielding on the Apollo spacecraft would have attenuated 400 rems to less than 35 rems, and to reiterate, the average yearly dose per person for background and man-made radiation is approximately 0.62 rems. Their contingency for this includes a quick trip back to Earth for medical care, and you'll find that on NASA's website. Given the level of technology regarding rocket propulsion then and now, the fact that the moon had no atmosphere and no magnetic field to protect it from SPEs, and that it would take 3 days to get back to Earth, NASA needs to redefine what a quick trip back to Earth is. Proponents of the Apollo missions say that 35 rems is safe for short durations, that is, if you believe the shielding capabilities of the Apollo spacecraft. The National Council on Radiation Protection and Measurement, NRCP, says that 35 rems is survivable, but it's obvious, as will be discussed in Chapter 5, that the LM's flimsy design and shielding would not have attenuated 400 rems or 960 rems to acceptable levels for the safety of the astronauts. For the most part, Earth's atmosphere and magnetic field protects us from these harmful rays, but outside of the Earth's magnetic field, there are some of the most penetrating forms of radiation and a hazard to many manned missions. During the 1950s, the only way to detect solar particles within SPEs was through ground-based instruments. These particles were secondary particles called muons, which had reached the instruments on the ground. But for these particles to reach the instruments on the ground, the solar particles within the SPEs had to have exceeded the MVE range with extremely high energies greater than 4 GeV to penetrate Earth's magnetic shield. So, if 30 MeV protons can penetrate the mid-deck of the space shuttle, it doesn't take much to determine what greater than 4 MeV particles can do to astronauts with the level of shielding that the Apollo spacecraft had. A minimum amount of aluminum wouldn't have offered any protection for the Apollo astronauts anywhere outside of LEO. The conflicting information between above quotes of 400 rems and 960 rems for the August 4, 1972 SPE, as well as what would have happened to any of the astronauts if they had been caught in this SPE, is disturbing. Given this conflicting information regarding SPEs and NASA's procedural protocols, the reality is that the Apollo astronauts would most likely have been vaporized. Proponents sneer when you mention the possibility of astronauts being vaporized by an SPE. However, since SPEs can reach into the GeV range, there is no shielding to protect the astronauts with present technology, so astronauts being vaporized is a real possibility. It has been rumored that the Soviets had sent several creatures and a cosmonaut to the moon with their Zond space program in September of 1968. When the craft returned and was retrieved from the ocean, the creatures and cosmonaut were rumored to have been vaporized, and the American government was notified about this. I haven't been able to substantiate it, so for now, it'll remain just that, a rumor. But the Soviet Zond space program did exist, and the official record does show that a mission with small creatures on board was sent to the moon and back with seemingly little or no harm to the creatures. In September 1968, they flew an unmanned Zond around the moon, and in November of the same year, another craft loaded with tortoises, flies, and worms took the same trip. Then for once, the Russians hesitated. They wanted more tests. The cosmonauts wanted to go, but they were held back. The Americans might still fail. It was better not to risk all so soon. Tortoises can survive thousands of times the radiation than humans, and rather than err on the side of caution, as the Soviets did by sending an unmanned Apollo spacecraft to circumnavigate the moon, the Americans instead sent the first manned mission, Apollo 8. And it would be interesting to know the real reason the Soviets hesitated. Coronal mass ejections. Coronal mass ejections, or CMEs, are believed to be associated with SPEs and are just as dangerous, though the actual mechanisms of this are still not understood. Coronal mass ejections consist of large balloon-shaped clouds of solar plasma and magnetic field that contain up to 10 to 16th grams of matter and reach speeds in excess of 2,500 kilometers per second. The kinetic energy alone is sufficient to boil the North Atlantic Ocean. CMEs are associated with solar flares and solar energetic particle events and occur most often during sunspot maximum. Most of the energy in such events is associated with CME and not the flare. One doesn't need to be an expert in space physics to know the consequences of being caught in the middle of a CME, which has enough energy to boil the North Atlantic Ocean. To reiterate, the Apollo missions supposedly took place during solar maximum. Proponents of the Apollo missions are quick to point out that SPEs and CMEs are not omnidirectional, thus insinuating the chances of being hit by one is minimal. It is true that SPEs and CMEs are not omnidirectional, but they are reflected by the sun's magnetic field, affecting a much wider area in the solar system, making any manned mission outside of LEO just as vulnerable no matter what area of the sun these emissions emanate from. Therefore, this would have increased the chances of an Apollo mission being hit by an SPE and CME. Although CMEs move slower, they can reach the Earth in approximately 48 hours, so there wouldn't be a lot of time for any manned mission in cislunar space to seek the relative safety of the Earth's magnetic field. Just like CPEs, the prediction of CMEs is difficult. In the 1960s, NASA had several observatories stationed around the world, and as the National Research Council reiterates, prediction of the solar storms is difficult even today. So SPEs and CMEs are a serious risk to any manned mission outside of LEO during solar minimum or maximum years. In other words, prediction of SPEs and CMEs when sending manned missions outside of LEO is far from being an exact science and not something that should be ignored when it comes to the safety of astronauts. Galactic cosmic rays. Now that we've established the hazards of sending manned space missions through the Van Allen belts as well as the dangers of SPEs and CMEs, the Apollo astronauts would also have to have contended with galactic cosmic rays, GCRs. There are two sources for GCRs, radiation that comes from the sun, called solar energetic particles, and radiation entering our solar system from all directions called galactic cosmic rays. GCRs contain extremely high energy protons, alpha particles, and heavy nuclei. Cosmic rays are measured in MeV and GeV range. They represent about a third of the radiation in space. Although GCRs are always present, cosmic rays from outside the solar system are at a minimum during intense SPE activity from the sun. As previously mentioned, the Apollo missions took place during that period of intense SPE activity. However, with that intense SPE activity comes solar energetic particles, another form of cosmic rays. Yet, the National Research Council has said that manned missions to Mars will require much more protection and shielding thickness to counter the steady GCR exposure as well as SPEs. A manned mission to Mars will take several months compared to a manned mission to the Moon, which would take 3 to 4 days. However, there's no reason to assume why the same level of protection and shielding shouldn't be applied to manned missions to the Moon, especially during extravehicular activities, EVAs, on the lunar surface, where astronauts have only their zipped-up spacesuits for protection against GCRs, SPEs, and CMEs. Mary Bennett and David Percy write, These might be technical terms used by experts, but when presented to the general public, there is a potential for the manipulation of reality through vocabulary. The dividing of space into cislunar space, the region of space within the orbit of the Moon, and deep space beyond lunar orbit, lulls the public into false assumptions concerning the safety of manned spacecraft and has little to do with the reality of space environment. When discussing shielding, NASA tends to use terms like cislunar space and deep space, giving the impression that radiation between the Earth and the Moon is more tolerable than between the Moon and Mars, as per the above quote. It's an attempt to differentiate space beyond low Earth orbit, giving the public the impression that the dangers of radiation in cislunar space is minimal compared to deep space, that is, in the case of a manned mission to Mars. There's no difference in intensities with SPEs, CMEs, and GCRs between the areas of the Earth, Moon, and Mars. You would require the same level of shielding for any manned mission, regardless of the duration and distance of the mission. As for the dosimeter readings of the astronauts, NASA has purposely released the average doses that the astronauts received during the mission, but the actual specific dosimeter readings for each astronaut are classified. It has been 50 years since the Apollo mission, so why the secrecy about the Apollo astronauts' dosimeter readings that is needed to be classified, especially considering that NASA has supposedly released the combined average doses the Apollo astronauts received? There can only be two reasons. One is that the readings don't exist, or two, they never went any further than low Earth orbit. It's interesting to note that the average Apollo 11 dosimeter readings are comparable to readings on the International Space Station in low Earth orbit. A quote here, a quote there. Anyone who's read any of the numerous books on radiation in general knows that the two scientists can agree on different effects of radiation on Earth, whether it's natural, background radiation, or man-made. Yet how interesting it is that few scientists who have studied NASA's data on the Van Allen belts, SPEs, CMEs, and GCRs agree on every aspect of them, while other scientists who haven't even been bothered to research it for themselves agree to its validity when reading other scientists' research papers on this. This method of peer-reviewed papers should be approached with caution, given some of the recent disclosures of fraud within the scientific community and the influence of fiduciary obligations. In the previously mentioned article online, Robert A. Bronig went out of his way to try to discredit anyone who questions the Apollo missions by labeling them conspiracy theorists, and then went on to rant about their supposed tactics. Bronig writes, "Absent the ability to perform a proper quantitative solution, the conspiracies are forced to look for circumstantial evidence. They can generally do little than point out what they believe to be suspicious activity or resort to quote mining." Quotes are used all the time by people on both sides of the discussion, including Bronig himself, and there's nothing wrong with it. But there's a reason he specifically mentioned the tactic of quote mining, since there are some very interesting quotes made by scientists and professionals themselves when specifically talking about the Apollo missions and related subjects, as these statements more than cast doubt on the validity of these missions. In fact, quotes can actually destroy decades of research. An example of this was recently revealed in the prestigious medical magazine, the Journal of American Medical Association, JAMA, when it disclosed how 3 Harvard scientists were paid approximately $25,000 50 years ago to falsify their research on heart disease. For the last 5 decades, hundreds of thousands of scientists, doctors, and journalists were manipulated into believing a fabricated story. It's disturbing that very few of these professionals questioned the findings of these 3 Harvard scientists. What is even more disturbing is the fact that millions of people around the world who trusted these Harvard scientists were possibly harmed by these trusted professionals. Therefore, thanks to Robert Bronig, we'll close this chapter by showing the importance of quote mining by professionals inadvertently on those purposes, show how quotes can undo decades of research by challenging established beliefs. Dr. James Van Allen regarding the radiation belts. Our measurements show that the maximum radiation level of 1958 is equivalent to between 10 and 100 Roentgens per hour, depending on the still undetermined proportion of the protons and electrons. Since a human being exposed for 2 days to even 10 Roentgens would have only an even chance of survival. The radiation belts obviously present an obstacle to spaceflight. Unless some practical way can be found to shield space travelers against the effects of the radiation, manned space rockets can best take off through the radiation-free zone over the poles. 10 Roentgens is 9.329664 rems, and 100 Roentgens is 93.296637 rems. As established earlier, the average yearly dose per person for background and man-made radiation in the United States is approximately 0.62 rems. As Braining will quickly point out, Dr. Van Allen mentions a human being exposed for 2 days, while the Apollo astronauts spent a total of 2 hours traveling the outer region of the outer radiation belt. However, we've learned that NASA doesn't fully understand the radiation belts, and there is evidence of electrons far greater than 15 MeV, which extends the Apollo shielding capabilities. So, 2 hours or less in the radiation belts may well have been enough to have seriously harmed the Apollo astronauts, that is, without even considering the artificial radiation belt formed by Operation Starfish Prime. Further, the Apollo missions apparently spent 15 minutes in the most intense inner-dominated proton belt, which NASA itself says manned missions must avoid. However, as has been established by J.R. White, NASA doesn't know for sure the energy fluxes of these high-energy protons and electrons in both the inner and outer radiation belts. So, 15 minutes in the inner-dominated proton belt may well have been enough on its own to have seriously harmed the Apollo astronauts, given their lack of shielding. As I mentioned earlier, it took over 30 years for Dr. Van Allen to refute his own statement about manned space missions traveling through the radiation-free zone around the North and South Poles. In response to a 1-hour documentary called Conspiracy Theory, Did We Land on the Moon?, shown on Fox TV in February 2001, Dr. Van Allen reportedly said this in an email. However, the outbound and inbound trajectories of the Apollo spacecraft cut through the outer portions of the inner belt, and because of their high speed, spent only about 15 minutes in traversing the region and less than 2 hours in traversing the much less penetrating radiation in the outer radiation belt. The resulting radiation exposure for the round trip was less than 1% of a fatal dosage, a very minor risk among the far greater other risks of such flights. I made such estimates in the early 1960s and so informed NASA engineers who were planning the Apollo flights. These estimates are still reliable. So now the Apollo spacecraft spent 2 hours in the outer electron belt? Again, it depends on the source. This data is supposed to have come from NASA, so why is there conflicting information? And as we've seen, estimates are anything but reliable. And where is Dr. Van Allen's scientific paper refuting his own work? To say it in an email doesn't qualify, and there are questions as to the source of this email. At any rate, an email refuting a previous scientific paper is not exactly considered part of the scientific realm. Given what we've established here, Dr. Van Allen's original remarks in his scientific paper in 1959 about manned missions traveling through the radiation-free zone over the poles would seem the most logical and safest, that is, going around the radiation belts, not through them. Barbara P. Pope writes, "The sight of Armstrong walking on the moon was so unbelievable and amazing that there were those who refused to believe the images they saw and swore that the landing was a hoax and a conspiracy." It's interesting that Pope, a retired employee of NOAA, actually said that it makes you wonder why a scientist would even mention the word conspiracy. Is she hinting at something? Quite possibly, as you'll see in her next quote. Apollo 11 turned out to be a string of lucky Apollo missions that were not hampered by space weather events, which was something of a miracle. Any number of space weather disturbances could have endangered the lives of the astronauts either directly or by damaging equipment. Now there's a quote that lacks confidence, if not downright skepticism, about the validity of the Apollo missions. On August 30th, 2012, NASA launched the Relativistic Electronic Proton Telescope REPT. A NASA article says that before REPT was activated September the 1st, 2012, solar activity on the Sun had sent energy to Earth, causing the two existing radiation belts to increase in size. According to NASA, it is this energy that caused the formation of a third radiation belt. NASA says that this newly formed belt lasted approximately 4 weeks. Here's proof that as recent as 2012, NASA had ever considered the possibility of a third radiation belt formed from solar storms. Then something happened that no one had ever seen before. The particle settled into new configurations, showing an extra third belt extending out into space. Within mere days of launch, the Van Allen probes showed scientists something that would require rewriting textbooks. This quote from the article on NASA's website throws into question decades of research regarding the Van Allen belts. And it's not a very confident statement coming from a space agency that claims it solved the problem of sending manned missions through the Van Allen belts 50 years ago. It further shows that NASA had no way of knowing if another radiation belt had formed by August 4, 1972 SPE, 4 months before Apollo 17. It also appears that NASA hasn't learned much from Operation Argus and Operation Starfish Prime either. As we've established with Operation Starfish Prime, as of 2012, that's 4 radiation belts, not 3. Kelly Smith, the NASA engineer in the YouTube video previously mentioned, uses terms like extreme radiation and dangerous radiation to describe the Van Allen belts. Further on his video, he says, "We must solve these challenges before we send people through this region of space," when talking about the Orion spacecraft. Apparently, they solved the problems during the Apollo missions, but for some reason, these problems need to be solved again? Given all the facts, the evidence proves that none of the Apollo missions traveled through the Van Allen belts. Chapter 5. Shielding for Radiation, Thermal Control, and Micrometeoroids. Some tinfoil should do it. As Chapter 4 has shown, the Apollo spacecraft had inadequate shielding for the radiation it would have encountered in the Van Allen belts, GCRs, SPEs, and CMEs. Also, as discussed in this chapter, the August 4, 1972 SPE had an intensity of 960 rems, that is, depending on your source. To attenuate 960 rems to 40 rems, an amount considered acceptable levels for the astronauts, the Apollo spacecraft would have needed approximately 4 inches of aluminum shielding. That's still a high level of radiation to be exposed to when encountering an SPE, given that the dosage accumulated would have depended on the duration of the astronauts had been exposed to in the intense radiation. Note: the standard allowable dosage for employees working with radioactive materials is 5 rems per year. Given the real possibility that the Apollo astronauts would have encountered an SPE, and that NASA says the CM shielding would have attenuated radiation down to approximately 40 rems, that's still a dose of radiation equivalent to 8 times the allowable yearly dosage as set by the governmental regulation agencies. However, the duration of exposure to 40 rems needs to be taken into consideration. The fact that there would have been substantial damage incurred by the astronauts remains uncontested, the main point being that no one, not even experts, can talk in definite terms regarding terrestrial and extraterrestrial radiation as its effects on people, especially those that were part of the Apollo missions beyond LEO. John H. Malden has a master's in physics and a PhD in science education and is also a former employee of NASA. His responsibilities included work on the Voyager missions. He made some interesting remarks about the required protection from radiation for manned missions. Malden writes, "By comparison, solar flares can deliver GeV protons in the same energy range as most of the cosmic particles, but at much higher intensities. Increase of energy accounts for most of the increased radiation danger because GeV protons or their products will penetrate several meters of material. As for GCRs, cosmic particles are dangerous, come from all sides, and require at least 2 meters of shielding all around the living organisms." Proponents of the Apollo missions have pointed out that Malden is talking about interstellar travel and that enormous distances between solar systems are far greater than interplanetary travel, therefore requiring more shielding than is needed for manned missions to the Moon and to Mars. Therefore, the proponents are insinuating that radiation intensities are different depending on the area of space that a mission is traveling through. That insinuation is partially true, but it does not represent the whole picture. Are SPEs any different in intensities between the Earth, Moon, and Mars? One could argue correctly that SPEs are more intense between the Earth and the Moon given their closer proximity to the Sun. In fact, when talking about SPEs, Malden points out that SPEs can give a dose of hundreds to thousands of rem over a few hours at a distance of miles from Earth. No one needs to be an expert to know what hundreds of thousands of rem over a few hours can do to human beings. As shown in Chapter 4, NASA tends to give the impression that by calling space between Earth and Moon cislunar space, the elements that could be encountered by manned missions to the Moon is somewhat less intense than deep space manned missions, which is not entirely accurate. Are GCRs any different in intensities inside and outside of our solar system? GCRs are no less dangerous in our solar system, even when we factor in the solar cycle of the Sun. In fact, when it comes to shielding spacecraft, especially unmanned missions anywhere in cislunar space and beyond, it is the mass and density of the material that is the important factor in protecting the astronauts. Ralph Renee writes, "It wouldn't matter if the shielding material was made of lead or not. Radiation shielding depends mostly on the mass and density of the material that is between the source and the victim. Lead is effective because of its high density. On an equal basis, a layer of water is even more effective, despite its lighter mass, but lead is less bulky. Of course, to launch a spacecraft shielded by the added weight of water or lead would far exceed the lift capabilities of any rocket design in existence. And as we have discussed in Chapter 2, the heavy lift capabilities of the Saturn V, the most powerful rocket ever designed and built, as is claimed by NASA, couldn't even make it to low Earth orbit because of its unstable F1 engines. Aluminum shielding thickness is most effective at stopping primary heavy nuclei, the type of cosmic radiation that causes the most damage to living tissue. Components of the annual cosmic ray dose equivalent versus shielding thickness are shown at a time of minimum solar activity. High-energy protons interact with shielding material to generate additional secondary particles. With about 7.5 centimeters of aluminum, the normal dose equivalent is reduced from 50 rem to 35 rem. Calculations for a very large solar flare series like the events of August 1972 show that the lethal unshielded dose of about 1000 rem is reduced to 40 rem with 9 centimeters of aluminum shielding. As has been made clear, the Apollo CM and particularly the LM had nowhere near the shielding necessary to attenuate radiation to 40 rems. However, the CM might have had the protection it needed had it stayed within the relative safety of low Earth orbit, well under the Van Allen belts and within some protection of the Earth's magnetic field. So, the only protection the CM and LM would have had with an SPE like the intensity of August 4, 1972 SPE is to avoid it, and given the level of technology used in the Apollo missions, that would have been impossible. NASA said that it had procedures for the astronauts to follow in the event of an emergency like encountering an SPE. For example, a radiation survey meter, RSM, is taken on each Apollo mission. The RSM is a direct reading dose rate instrument that allows the crewmen to determine radiation levels in any desired location in their compartment. The crewmen would use the RSM to find a habitable, low-dose region within the spacecraft in the event of a radiation emergency. When one checks out the actual dimensions of the crew compartments in both the CM and LM, one has to wonder where exactly a habitable low-dose region within the spacecraft in the event of a radiation emergency would be located. Aside from exposures to the Van Allen belts, GCRs, SPEs, and CMEs, the Apollo spacecraft would also have had to contend with thermal control and micrometeoroids. For thermal control, there's still a debate as to the best methods of controlling spacecraft temperatures while in low Earth orbit and beyond, although seemingly this debate was resolved during the Apollo missions. And it is common knowledge micrometeoroids can be a hazard to any space mission, whether manned or unmanned. With an adequate shielding, a high-velocity object in space can penetrate a spacecraft with catastrophic consequences, in addition to what it would do to any astronaut on an extravehicular activity EVA. We will be discussing thermal control and micrometeoroid protection in this chapter. Any one of these 6 base environmental elements, the Van Allen belts, GCRs, SPEs, CMEs, thermal control, and micrometeoroids could have ended a mission in minutes or even seconds, let alone encountering all 6 of these elements at once. Thus, to appreciate the complexity and seriousness of any of these elements in the space environment, we must first review the shielding of both the CSM and LM. As we continue on, it will become evident that neither the CSM or LM had anywhere near the protection needed for any of the elements of space environment as mentioned above. Command and Service Module dimensions and shielding. The CM consisted of two sections, the SM and CM. The SM was 24.93 feet in length with a diameter of 12.79 feet. It was made of 1-inch thick walls comprised of aluminum alloy honeycomb panels. It was divided into 6 compartments, 4 of which carried the propellant needed for the 20,500-pound Thrust Service Propulsion System SPS engine. The 5th compartment contained the fuel cells and the reactants needed for the electrical power, life support systems, water management, and air temperature regulation. On Apollo 11, the 6th compartment was left empty. On later missions, the 6th compartment was used to carry the Scientific Instrument Module, SIM. The SM also carried most of the communications as well as the reaction control system for attitude control. The aluminum alloy honeycomb panels would have needed to protect the propellants and communications equipment for all of the 6 space environmental elements mentioned. The CM had a height of 10.56 feet with a diameter of 12.82 feet. Its structure consisted of an aft heat shield, the pressurized primary structure of the crew compartment, a central heat shield over the primary structure, and a forward heat shield which housed the docking mechanism and the parachutes needed for the eventual splashdown into the Pacific Ocean. The inner pressurized crew compartment was constructed with lightweight double-skin aluminum alloy material. The non-pressurized central heat shield structure consisted of fiberglass honeycomb bonded to a steel honeycomb material covering the primary structure. It is this outer layer of the CM that NASA claims provided protection from radiation, thermal, and micrometeoroid exposure. The combined thickness of the material used to construct the inner and outer walls was from 1.10 to 1.5 inches thick. There were 5 windows, all made with triple layers of glass, the outer one being 3/4 inches thick. The actual space available to the astronauts was approximately 210 cubic feet, which is about the size of an average car. The overall protection of the CM consisted of the forward heat shield, the material around the main part of the spacecraft, and the aft heat shield. The aft heat shield's primary purpose was to provide protection from the fiery re-entry into Earth's atmosphere. The aft shield was made of material that charred and burned away in a process called ablation. The material used in the aft heat shield was up to 2.5 inches thick. For the purpose of this chapter, our discussion will focus on the effects of radiation, heat, and micrometeoroid impacts on the CM and LM in cislunar space. The aft heat shield will be discussed in detail in Part 2 of this series. Lunar Module dimensions and shielding. Like the CM, the LM had 2 sections, the descent stage and the ascent stage. The descent stage was approximately 12 feet in diameter and 31 feet diagonally across the landing gear. It was divided into 4 quadrants which contained the 4 propellant tanks and the supercritical helium tank. It also contained the 10,000-pound thrust engine used for lunar orbit and descent to the lunar surface. The primary structure consisted of aluminum alloy which was also covered with 16 layers of golden mylar aluminized foil. It is these layers of mylar aluminized foil around the descent stage which is supposed to have provided the necessary thermal and micrometeoroid protection. The ascent stage had a height of 12.34 feet. This contained the crew compartment which had a horizontal shape within a diameter of 7.67 feet and the length of 3.5 feet. It also contained a 3,500-pound thrust engine needed for launch from the lunar surface. The structure consisted of aluminum alloy and had 2 triangular forward-facing windows and 1 docking window above the commander's station. The skin of the LM cabin was just 0.012 inches thick. In the end, the lander became a strange mix of strength and fragility. The skin of the descent stage was only a mylar wrapping stretched over a frame. In the ascent stage, the walls of the crew cabin were thinned down until there was nothing more than a taut aluminum balloon, in some places only 5/1000 of an inch thick. Once, a workman accidentally dropped a screwdriver inside the cabin and it went through the floor. Now in space, it seems deceptively flimsy. When the cabin was pressurized, the front hatch bulged outward. That had scared John Young, who was in the command module wearing nothing but a pair of long johns. He was up muttering, "I didn't know I was volunteering to go on this damn thing in my underwear." No wonder Jim McDivitt called this LM the tissue paper of spacecraft. But it was sturdy enough, even more than enough, for the moon. Directly over the crew's heads was the hatch that provided access when docked to the command module through a tunnel. The crewmen stood in the lunar module looking forward through a small triangular window on each side, with the commander on the left and the LM pilot on the right. The external skin of both stages was paper-thin aluminum. The lower stage was covered by multiple layers of gold mylar insulation. You could easily poke a pencil through the side of the spacecraft. Portions of the interior were covered with netting to save weight and catch anything that might fall into the nooks and crannies inside of the LM. Designed to operate only outside the Earth's atmosphere, the LM looked ungainly and had no heat shield and was incapable of safely entering the Earth's atmosphere. As you can see from the above section, the Apollo CM had nowhere near the shielding protection necessary to attenuate radiation to acceptable levels. Add to this the windows in both the CM and the LM and the overall shielding necessary to protect the astronauts from intense radiation and/or micrometeoroids didn't come close to the level for protection that would have been needed when compared to what was mentioned above by John Malden. The materials used to make the CM walls were 1.5 inches thick, which included the aluminum alloy and honeycomb panels. Aside from John Malden's recommendations, this doesn't even come close to the 4 inches of aluminum or more that would have been needed to attenuate intense radiation encountered in SPEs to acceptable levels for the astronauts' safety. As for the LEM, the walls were so thin that you could easily poke any object through them, causing a rapid decompression, instantly killing the crew had they not been wearing their spacesuits. In other words, all that separated the two astronauts in the LM from that of the vacuum of space were the cabin walls equivalent to the thickness of 3 layers of kitchen foil. The LM and its flimsy design will be discussed in part 2 of this series. In the next section, we'll discuss the issue of temperature in space, including whether it's hot, cold, or neither, and why the importance of thermal control would have been another necessary part for any Apollo space mission to have succeeded. Temperature in space. We often hear about the extreme coldness of space and how anything exposed to this environment will freeze. That's not entirely accurate in our area of space. Earth's atmosphere diffuses heat more evenly because of conduction and convection. But the vacuum of space, for the most part, is devoid of matter, so therefore it can be better described as neither hot or cold. Being that the Earth and the Moon are approximately 93 million miles from the Sun, the effects of temperature are a constant threat for space missions in LEO and beyond. In LEO, spacecraft would spend half of their orbits exposed to the Sun with temperatures on the outside of the hull reaching as high as plus 200 degrees Celsius, while reaching minus 200 degrees Celsius in LEO away from the Sun. But in cislunar space, the aircraft would be constantly exposed to the Sun, increasing temperatures on the outside of the hull. In addition, the area of space around the spacecraft would act like an insulator, adding to the problem of heat buildup within the crew compartment. The analogy of a thermal flask best illustrates the problem. The area between the inner and outer sections of the thermos flask is devoid of any of the outside atmosphere, in effect a vacuum. Therefore, heat in the inner section cannot be conducted outside, keeping hot liquids close to the same temperature for hours. This can be compared to the vacuum of space around the spacecraft. The spacecraft would lose heat through radiation, much like the thermos flask. So in effect, the vacuum around the spacecraft becomes an insulator. Here's what's going on. Most of the gas in space is too thin to warm anything up. Essentially, there is not enough gas particles to bump into and transfer the heat to an object. So if you were in space, but shielded from the Sun, you would radiate away nearly all of the heat quickly and cool to the cosmic background temperature. Step or float into the Sun, and you'll be warmed. Either way, you'll need lots of protection. If the Apollo missions had really circumnavigated the moon, the problem would be to have to prevent the CM and the LM from getting too hot or too cold. The Apollo spacecraft would constantly have been bombarded by the sun's rays on one side of the outer hull en route to the moon, with the same conditions on the way back to Earth, reaching temperatures as high as plus 200 degrees Celsius or more. The opposite side of the CM and the LM would have been cold by comparison, since the vacuum of space cannot conduct heat from the side facing the sun. In addition to this, the CM crew compartment atmosphere would have acted like a conductor, heating all areas of the CM interior. Although there would have been heat loss through radiation on both sides of the CM and LM, the constant bombardment of the sun's rays would have been a constant source of heat, causing a buildup of temperatures to dangerous levels that would have eventually killed the astronauts. As the above quote says, "Step or float into the sun and you'll be warmed." Either way, you'll need lots of protection. However, NASA says that it solved this problem through environmental and thermal control. The environmental and thermal control aspects of any spacecraft depends on whether its mission is in LEO or beyond. We'll discuss the thermal control aspects of the Apollo missions in the area of space between the Earth and the Moon, that is, cislunar space. The Apollo spacecraft environmental and thermal control, deflecting radiation and regulating the temperature from the sun's heat as well as heat produced from the inside of the CM would not only have been imperative for the safety of the astronauts, it would have been essential for the proper functioning of the power systems of the Apollo spacecraft. The instruments and computers for both the CM and LM would have needed to be maintained at a temperature conducive to the astronaut's safety. Since conduction and convection are absent in the vacuum of space, the thermal control system had to be designed to reject the excess heat into space while maintaining appropriate temperatures inside of the Apollo spacecraft for all phases of the mission. Therefore, this along with many other considerations would have been needed to have been factored into the design of the CM and LM. A malfunction of the environmental and thermal control system alone would have ended any Apollo missions in hours, possibly minutes. Hence, considering the vast distances between the Earth and the Moon for our level of technology, there would have been no possibility of an Apollo mission making it back to the Earth safely in event of an environmental and thermal control system failure. In LEO, the astronauts may have survived a partial failure of the environmental and thermal control system in the CM, where emergency procedures could at least be implemented for a re-entry and an eventual splashdown. The atmosphere revitalization system and the thermal control system is another of many aspects of the Apollo CM and LM that would have had to work to near perfection since, as we previously established, there is little or no redundancy in the design. Atmospheric Revitalization System. The Atmospheric Revitalization System, ARS, was there to regulate the temperatures for the heat produced inside the CM. For example, heat produced from the instruments and components necessary for the proper function of the spacecraft would have had needed to be radiated and/or routed to mechanisms that would have rejected the heat to the vacuum of space. Carbon dioxide and humidity produced by the astronauts would have needed to be removed too. All of this would have had to be done on a continuous basis. The ARS involved heat exchangers, electrical heaters, and water glycol coolant loops. The heat exchangers were used to heat the crew compartment if needed, with electrical heaters used as backup for more heat if necessary. To help regulate the temperatures for astronaut safety as well as for the proper function of the CM and LM, coolant loops would have cooled the electronics. This excess heat was then routed to radiators in the service module and emitted through radiation out into space. This, of course, is how the ARS was supposed to have worked according to the few NASA documents still available. Thermal Control System. The Thermal Control System, TCS, was used to help regulate and deflect heat, mainly from external sources such as the sun. The design of the Apollo spacecraft, TCS, included mylar foil coating applied to most of the surfaces of the CM and LM. The mylar foil coatings help to deflect heat from the sun's solar rays. However, degradation of the thermal coatings would have needed to be factored in on any of the Apollo missions, since long-term working solutions for these coatings had yet to be found. The boost protective cover over the main CM structure helped to protect the thermal coating during launch, which was then jettisoned before orbital insertion. But given the unpredictability and variations of the harsh environment of space, calculations needed to be precise, since any estimates would have been inadequate. Any encounter with one of these 6 space environmental elements would have required immediate action on the part of astronauts, although GCRs would have constituted a constant threat. This would have required the response time of an autonomous computer equipped with sensors capable of determining the degradation or damage done to the protective coating and/or shielding, and then communicating that information to the astronauts. Of course, as has been established in Chapter 3, the AGC do not have this capability. As one side of the CM and LM would have been facing the Sun en route to the Moon, a method had to be devised to even out the heat around the CM and LM's hull. To prevent one side of the spacecraft roasting and the opposite side freezing in the constant sunlight of cislunar space, it was oriented with its principal axis perpendicular to the ecliptic, then set on a 20-minute cycle for passive thermal control (PTC) in a regime more popularly known as the barbecue mode. This had to be established before the astronauts could retire for the night. After launch into LEO of the Saturn V, it would have been long before the CM had fired its engines for TLI into cislunar space, so if a passive thermal control (PTC) was necessary to help even out the temperatures of the CM, one wonders why this needed to be established before the astronauts could retire for the night, and not before, since it would have taken long for the CM to heat up owing to the constant rays of the Sun shortly after leaving LEO. But PTC was hardly a solution to the problem of protecting the CM from the constant heat of the Sun, and given the degradation process of the reflective mylar covering of the outer hull, this further exposed the CM to extreme heat. The slow roll of the CM and docked LM along its longitudinal axis for PTC also has its own problems. PTC supposedly worked well during the Apollo 8 mission, but according to NASA, PTC caused other problems that affected the longitudinal axis of the spacecraft during later Apollo missions, since these missions involved the LM unlike Apollo 8. This added further to problems in navigation, which could have required even more course correction. Given the tasks of maintaining precise navigation, nothing short of an autonomous computer equipped with sensors interfaced with the navigation and flight control systems of the CSM would have sufficed. As is being established in Chapter 3, crew interface was necessary for making course corrections, which is nowhere near as autonomous as the AGC should have been, aside from the fact that this computer had little or no memory for any of the tasks it was expected to do. According to NASA, the interior of the command module must be protected from the extremes of the environment that will be encountered during a mission. These include the heat of boost, up to 1200 degrees Fahrenheit, the cold of space, and the heat of the directed rays of the Sun, about 280 degrees below zero on the side facing away from the Sun, and 280 degrees above zero on the other side, and most critical, the intense temperature of entry, about 5000 degrees Fahrenheit. The insulation between the inner and outer shells, plus temperature control provided by the Environmental Control Subsystem, protects the crew and sensitive equipment during the CM's long journey in space. There seems to be more conflicting information regarding the heat outside of the CM facing the Sun. As per the above quote, NASA indicated it was up to 280 degrees Celsius, while other sources mentioned 200 degrees Celsius. But clearly, NASA is indicating that the Apollo astronauts needed to be protected from the extreme heat of the Sun. NASA contradicts itself yet again. As we discussed in Chapter 3, Apollo 13 had a rupture in one of the oxygen tanks in the SM. As a result, the astronauts had to power down the CSM. This forced the astronauts to move into the LM while coasting back to Earth. However, it is claimed that powering down the CSM caused the temperature to drop within the crew compartment. Aboard Odyssey, the crew too had been discussing their options. Oxygen tank number 2 was gone, its contents vented to space, but the contents of tank 1 were bleeding away. Jack Swigert was the onboard expert in the CSM systems, but all three knew the basics of physics. When the pressure fell to about 100 pounds per square inch, 689.5 kilopascals, It would be incapable of providing a supply to the fuel cells or to the cabin, and the temperature too was going down. As Swigert powered down the systems in the command module, it was getting colder, down already to 58 degrees Fahrenheit or 14.4 degrees Celsius, and noticeably chilly. Now the question is, if the Apollo 13 CM crew compartment became noticeably colder, what about the heat from the sun's rays that were constantly bombarding the side of the CM and the LM? Are we to believe that since there was no heat being produced by the CM systems after it was powered down, that the heat from within the crew compartment was now radiating heat into space faster than the buildup of heat from the sun's rays? Heat from the sun that was bombarding the spacecraft hull to temperatures of about 280 degrees Celsius or more? And what about the power systems of the LM? They would have been powered up, so wouldn't they have produced sufficient heat to at least counter some of the heat lost from the CM? If the heat from within the CM was radiating at faster rates than the heat from the sun, then there wouldn't have been a need for the PTC, or at least it should have been slowed down in order to utilize the sun's rays to warm the CM, since according to NASA, there was a concern over the CM systems getting too cold. Incredibly though, we are told that Apollo 13 continued with its PTC even when faced with cold temperatures. And even if the PTC was slowed or stopped periodically, that raises yet another issue. Given that the CM was now vital to the astronaut survival, and that would have remained docked to the CM for most of the mission back to Earth. The fact that the LM structure had even less protection for the astronauts than that of the CM, the LM walls having the thickness of 3 layers of kitchen foil, PTC, according to NASA, would have been a reasonable method for the LM. But now, this would have been counterproductive for the CM, since the CM and LM were docked for most part of the Apollo 13 mission. Thus for Apollo 13, PTC works for one spacecraft, but not for the other spacecraft docked to it. Therefore, once again, NASA contradicts itself. PTC would not have worked. As has been discussed so far, the CM and LM had nowhere near the protection necessary for any one of the 6 elements that could have been encountered in cislunar space. And, in fact, PTC would not have been a solution to the problem of evening out the heat from the sun around the hull of the CM and the LM either. Ironically, that barbecue mode we mentioned earlier, rotating the unprotected craft, actually would have ensured that the Apollo astronauts were like chickens on a spit, cooked, fried, baked, radiated, call it what you will, on all sides. The crew would have been better protected from the solar radiation by not rotating the CSM and using an appropriate shield on the sunward side of the craft. Therefore, since the PTC is not an effective way of evening out heat around the spacecraft, then the ARS and TCS would not have functioned as they were designed to. One system has to complement the other, or the whole system fails. As for the equivalent of 3 layers of kitchen foil surrounding the LM, and whatever protection NASA claimed it offered, would have led to disaster by any of the astronauts accidentally putting his foot through one of the side panels. NASA reveals it knew little about the space environment. During testing, it was discovered that extreme temperatures could have damaged the heat shield, making a safe re-entry into Earth's atmosphere impossible. This was discussed during the Apollo 13 mission after one of the oxygen tanks ruptured. There were other considerations too. Jettisoning the service module would expose the base of the command module to an untested environment. Although the heat shield embraced the entire exterior of the conical structure, the main defense against frictional heating on re-entry was a convex base. To expose that to the extreme temperatures of space would be unwise and risky. Moreover, no one knew the effect of jettisoning the service module would have had on the command module. Better to be close to home when that event was necessary, just before entering the atmosphere. From the quote, we learn of NASA's concern about exposing the command module to an untested environment. However, this untested environment was supposed to have been determined during the testing phase of the CM's heat shield in NASA's vacuum chamber, which is supposed to have been able to simulate most conditions of space. But if NASA was really so concerned about this untested environment, then it shouldn't have sent any manned mission without first testing an unmanned Apollo mission beyond low Earth orbit to circumnavigate the Moon. NASA claims to have completed 9 successful manned missions beyond LEO, 6 of which landed on the lunar surface, while admitting their knowledge of cislunar space was limited. Micrometeoroid shielding. This chapter has already revealed the inadequate shielding provided for many of the elements in the space environment for the Apollo astronauts, which was also including the provisions of shielding for micrometeoroids, and as been established, the LM had far less protection than that of the CM. Further, when looking into the data regarding micrometeoroid shielding, again we find incomplete information and/or missing documents. Given that the space missions, manned or unmanned, were in their known infancy in the 1960s and 1970s, and little or nothing was known about the elements of space environment talked about in this book, NASA further realized that it needed to address the issue of micrometeoroids. A micrometeoroid impact alone would have been disastrous for any of the Apollo missions. With the shielding used in the CM and the LM, there was no redundancy. Any failure of one aspect of the Apollo spacecraft shielding would have meant an abrupt end for any mission. NASA launched a series of satellites called the Pegasus missions to collect data on the thermal effects on coating surfaces, radiation effects on instruments, and micrometeoroid impacts. There are no long-term solutions to the effects of the thermal environment coating applied to spacecraft hulls, as has been established in Chapter 4. NASA didn't have the equipment necessary to detect radiation intensities beyond a certain level, therefore further eroding the mylar coating on the spacecraft hull. We'll now concentrate on the Pegasus mission's main purpose, which was to collect data on micrometeoroid impacts. The Pegasus missions. NASA launched 3 satellites in the Pegasus missions program on the Saturn V rocket, along with a boilerplate CSM, non-functioning CSM. The boilerplate Apollo spacecraft were used in numerous tests on the ground as well as in LEO. Of the boilerplate CSMs launched to LEO, 3 of them were used for the Pegasus satellites, which were located in the empty service module. The first Pegasus satellite was launched with Apollo 9, SA-9 on February the 16th, 1965, while the second was launched with Apollo 8, SA-8 on May 25th, 1965, and the third was launched with Apollo 10, SA-10 on July 30th, 1965. Note, Apollo 9, SA-9 was launched first due to a delay with Apollo 8, SA-8. These missions are not to be confused with the later manned missions of Apollos 8, 9, and 10. In Earth orbit, the Pegasus satellites extended its folded arrays, which reached approximately 95 feet in length. The arrays were designed for detecting and collecting data on micrometeoroid impacts, and there were additional sample protective shields that were mounted on the arrays. These sample protective shields were designed to be retrieved from a manned mission for further detailed analysis. The design and data from these sample protective shields were to be incorporated into the shielding of the Apollo missions. The whole point of the Pegasus missions was to gain data in support of the Apollo moon missions. However, the Pegasus missions went no higher than 500 miles in orbit, which meant that they were nowhere near the area of cislunar space in which the Apollo missions would have spent the bulk of their time. Data from within 500 miles in Earth orbit would have not sufficed for missions planning a 480,000-mile round trip. That's an area of cislunar space covering millions of square miles. Moving the goalposts. The sample protective shields installed in the Pegasus arrays were to be retrieved by one of the manned Gemini missions, but were not for some reasons ever explained. Although data from sensors was obviously stored, vital information from any retrieval of these panels was lost. NASA worked on a probability basis, which is the norm in a lot of industries, for example aircraft manufacturers. But by the 1960s, aircraft manufacturers had decades of research and data to use as a probability factor. However, at the time of the Apollo moon program, NASA had at best several years of research and data for its manned space program. So, the probability factor for manned space missions is an unfamiliar environment with such little research and data becomes more of an educated guess at best. The original failure criterion for the SPS propellant tanks was perforation of the SM honeycomb skin panels. Because the failure criterion was too stringent to meet the desired probability of mission success, engineers considered an alternative. If the original criterion had remained, the test shown in Figure 4 would have been an SPS tank failure. This quote is an indication of the strategy NASA used. If the criterion was too stringent for the mission success, then NASA changed the criterion, hence moving the goalposts. This is a strategy prevalent with much of the technology used in the Apollo moon missions, some of which have been shown in this book.